hear you perfectly. Can you hear me? Wonderful, wonderful. So I'm going to go full screen now, okay? Okay. Oh, okay, okay. And then I'll go full screen.
Good morning to all the faculty members, respected guests, and beloved student out there. Today is the second day of our conference, ICEIS 2023, and third day of the centenary celebration of Chemical Engineering, Department of Jadavpur University. The goal of ICES 2023 is to offer teachers, researchers, academics, engineers to form a forum to discuss the most recent advancement in the field of chemical engineering. So without further ado, we will begin our plenary session part. First, I would like to call upon our esteemed speaker, Professor Kamalesh K. Sirkar, to commence his discussion. Kamalesh K. Sirkar is a distinguished professor of chemical engineering at New Jersey Institute of Technology, author of 218 refereed publications and 40 patents. He had advised 40 PhDs, 47 MSs, and 28 postdocs. He was the editor-in-chief of Current Opinion in Chemical Engineering during January 2011 to June 2021. He co-edited the Membrane Handbook in 1992, which was reprinted in 2001 and 12. He pioneered the concept of membrane contactors among us. A number of technologies developed by him have been commercialized as well. A fellow of AAAS, AICHE, National Academy of Inventors, and North American Membrane Society, he has received, among others, 2005 AICHE Institute Award for Excellence in Industrial Gases Technology, 2008 Clarence Gerhold Award of the Separation Division of AICHE, and 2007 Alan Michaels Award for Innovation in Membrane Science and Technology. Sir, we would love that you should commence your discussion. Thank you. Sir, can you kindly start the presentation? We are waiting. Thank you.
You can see my screen now, right?
Yes, sir. We can see it well.
Yeah. Professor Chakrabarti, fellow chemical engineers, ladies and gentlemen, good morning to you. Although it's almost midnight here in Jersey. I am so happy to participate in the centenary celebrations of Chemical Engineering Department at Jadavpur University. That's a historic occasion. And what I'd like to do is I'd like to bring to your attention very quickly some of the research that is going on in our laboratory in search of perfect membrane separation processes. And I'll focus on 5 areas. Hopefully, I'll be able to cover them quickly. In each case, there would be a different situation. For example, in the first one where we are trying to separate hemoglobin and BSA, the membrane is not perfect, but we are trying to make the membrane separation process perfect. In the second one, reverse osmosis-based organic solvent mixture, the membrane is perfect. You will see amazing results where one pure solvent is obtained. In the third one, the membrane is perfect, but in the operation of the membrane fouling affects the separation. In the fourth one, you will see that adsorbents are coming to the rescue of membranes. And the fifth one is a different category altogether. Hopefully, I'll be able to talk to you about that. The first one deals with separation of hemoglobin and BSA. These two proteins have molecular weights that are very close to each other. They differ only by 2000. Ultrafiltration is normally not used for separation of such kind of protein mixtures. And there is a technique called high-performance tangential flow filtration, which has substantially improved the capacity of ultrafiltration membranes to separate closed mixtures, and they can get selectivities around 50, 70, and so on and so forth. And there are efforts that have been made to make isoporous block copolymer membranes having a particular pore size. But then you'll have to make a separate membrane for each different separation that you are dealing with. We avoid all of those problems by using the so-called internally staged ultrafiltration technique, which our group developed quite a few years back, and others have studied it also. And now companies are developing larger devices. So what it does is, if you have, say, one membrane, let us say it is giving you a 70% rejection of say, BSA, which is being rejected. And then the permeate from the first membrane is imposed on the second membrane, and the permeate from the second membrane is imposed on the third membrane. Mind you, these membranes are all placed right above each other. It's a very simple, just putting three pieces of papers on top of each other. And we are able to get very highly purified hemoglobin here, and we are retaining BSA, and you will see what kind of separation we are able to achieve here. Essentially, as you start putting one membrane on top of the second membrane and then another one, and you will have three membranes and achieve virtually step function separation. Here is I wonder what, there it is. So we have three membranes of ultracell. These are made by Millipore, or Omega made by Paul Corporation. These are 100 kilodalton membranes. And remember, hemoglobin BSA molecular weights are around 66,000 Dalton, 64,000 Dalton. So the selectivity of one membrane is not necessarily very high, but you control the pH, you control the ionic strength, and you control the pressure, and you can significantly improve the selectivity. Now, what I'm showing here at the top left corner is that a single membrane gives you pretty high retention of BSA, which is being rejected because it has negative charge, and the membrane has negative charge. And when we have three membranes, we are having virtually complete rejection. And we can have selectivities that I show to you on the right-hand side as much as 6,000, and it's decreasing because selectivity is as defined, depend on the concentrations. And still, even at a dye volume of 10, you are achieving very high selectivity of 80. And you will see in the next slide what kind of purity of BSA is being achieved. See, with three membranes, we are achieving 99.5% purity. We are also achieving 99.5, 99.7% retention of BSA. And the purity of hemoglobin in the permeate, because hemoglobin concentrations in the feed were low, are at the level of 97, 98%. So overall, what we are saying is BSA is being essentially rejected and retained, and with a very high percent retention and significant purity, and we are getting a reasonably pure permeate in terms of hemoglobin. And this is an important result in the sense that conventional ultrafiltration membranes can be configured to carry out such very close separation. So in separations, you have A and B. Question is, can we separate A and B completely apart and get pure A and pure B? This is a step in that direction. I'm going to switch the topic and start talking about something else. You have organic solvent mixtures, and you'd like to separate them by reverse osmosis. Is there any membrane that can do it? And here is one of those membranes. Perfluorodimethyl dioxyl tetrafluoroethylene PDD-TFE. This is the dioxyl group here. This is the the PTFE, the TFE group here. And if we take, say, a copolymer where this dioxyl group is about 87% and this is about 13%, and then we get very interesting properties. More importantly, whether the M value is about 65% or 87%, these polymers have very high free volume fractions, 32 to 37%. The only polymer that has a higher free volume fraction is PTMSP, polytrimethyl propyne, and they have very high permeance of oxygen. And even though the average free volume dimensions are pretty large, the oxygen-nitrogen selectivity is significant. And that is because these membranes are operating with a very significant selectivity for the Langmuir sorption type. Normally, membranes would have only Henry's law sorption, but these large free volume polymers have a significant amount of Henry's sorption, and you will see the interesting results that are following from this. And remember, they're very hydrophobic and cannot be dissolved by any solvents except perfluorosolvents. So they're ideal for reverse osmosis separations of organic solvent mixtures. I'm going to show you an example from a not so recent article came from Georgia Tech, who are doing a lot of research in separations of organic solvent mixtures. So they have a mixture of paraxylene and orthoxylene. They start with a 50-50 and they're coming up to 81% using a carbon molecular sieve membrane prepared out of pyrolyzing of PVDF polymers. And interestingly, remember the radius estimates of free volume openings, it's 3 to 4 angstrom in regular glassy polymers. Here it is substantially higher. And if most organic solvents are to be thought of as 5 to 7 angstroms in spherical model, they'll slip through our CMS7, this perfluorodioxyl copolymer membranes. And so if we are going to have any selectivity, it's going to be primarily due to solubility selectivity. And that's what I'm going to show you right now. So here we have simple flat membranes of this PDD-TFE polymer on an expanded porous PTFE substrate, and you apply substantial pressure on the feed side. And for 3 different compositions of the feed solution, 75, 90, 95 weight percent toluene in feed, and the rest being NMP, you're getting pure toluene in permeate. This is, of course, when just pure toluene is used through the polymer. Naturally, the flux is low because you have significant osmotic pressure limiting it. The question is, why is that? If you look at NMP, which is right here, and toluene, which is right here, their physical dimensions are not that far apart. I will also invite your attention to DMF dimensions or DMSO dimensions. These are also not that far apart. And yet, if we run experiments with toluene DMF, toluene DMSO, pure toluene would be coming out. And we verified an important factor named, something happened here. Let me switch on to methanol NMP mixtures. Remember, methanol is highly polar, NMP is highly polar, and their polar component of the solubility parameter 12.3 is identical. And yet, if you take feed mixtures of 75 weight percent methanol in feed and 90 weight percent methanol in feed, you're getting pure methanol. Very interesting. Why? And there have been some studies of pure organic vapor permeation through these perfluoropolymers, and people find that the only way they can describe the transport of these pure organic vapors is if they assume that there is significant amount of dimerizations of these protic organic solvents like methanol, ethanol, etc., etc. And so we carried out sorption studies of a methanol NMP mixture, 90 methanol, 10 NMP, and we dissolved whatever has been sorbed there in an headspace apparatus at a high temperature. And what did we find? Pure methanol is coming out. And so what we are postulating is that a very large fraction of methanol is dimerizing. It has a capacity to dimerize. NMP doesn't, because NMP is aprotic. And we have found it for other aprotic polar organic solvents as well. We have found exactly similar behavior with ethanol NMP. With high ethanol concentrations in feed, we are getting pure ethanol in permeate, but not for lower concentrations. For lower concentrations, the mixtures go right through. We checked it with sorption behavior, and we can see the polymer is really sorbing only ethanol, which must exist in the dimer form to be sorbed so effectively in preference to NMP. Here is an even more interesting result. We have a mixture of ethanol and butanol. If you have very low concentration of ethanol and high concentration of butanol, your permeate is pure butanol. On the other hand, if you have very high concentration of ethanol in feed and very low concentration of butanol, you see pure ethanol in feed. These things can only be explained on the basis of dimerization of each of these alcohols. And we made sorption studies, and it showed that if the ethanol concentration is very high in the feed, the sorbate composition is going to be pure ethanol. If butanol composition is very high in the feed, we'll have pure butanol in the sorbate. So this is an interesting situation where a membrane is actually perfectly selective for a particular organic solvent over other organic solvents, but there are significant limitations. This is a very interesting area because perfluorocopolymers don't behave like hydrocarbon-based hydrophobic polymers, and a lot more needs to be studied and learned, and we are, of course, looking for resources to do that. I'm going to switch to some other topic. Everybody is studying, it seems, desalination, and membrane distillation is a major area. The interesting thing about it is that what we have is a porous hydrophobic membrane, and you bring, say, hot saline on one side. Unless the pressure is very high, the saline cannot enter the pores of this hydrophobic membrane, but water vapor would be generated from this hot saline, and if you keep cold distillate on the other side, hot saline, the water vapor would be condensed. So that would be a very nice way of carrying out distillation of water. You can have vacuum on the other side, and you can condense the water vapor at some other place. We have studied both, but we have studied this technique extensively. Now, there are two items to remember here. As you start taking water out of here, saline waters often have scaling salts, calcium carbonate, calcium sulfate, and they will start precipitating on the membrane, and most people don't pay attention to these things. They're going about making this membrane, superhydrophobic membrane, that membrane, and so on and so forth. And if you take seawater at 3.5% salt and you have to go to 25 weight percent salt, you will precipitate virtually all of the calcium carbonate and calcium sulfate on the membrane. So you have to have arrangements to take care of them. Secondly, the heat for evaporation is coming from the sensible heat of this brine, and so therefore its temperature is coming down. You would like that temperature on the surface of the membrane to be high so that the vapor pressure is high, so that the flux is high. And so what we did was we had porous polypropylene hollow fibers, and we had one of the companies plasma polymerized a fluorosilicon coating on that with a gap like this so that it kind of tends towards superhydrophobic behavior. Much more important is we have these hollow fibers, and the hot brine is coming in cross flow. So there are many flow separation points. So we are generating secondary flows, eddies that are scrubbing the surface of these hollow fibers. And when you have thousands of these hollow fibers next to each other, so the motion of these flexible hollow fibers, which are almost like cantilever in the flow system, creates an enormously turbulent flow situation, except In fact, you are actually flowing the brine at laminar flow at Reynolds numbers of no more than 40, 50, 60. You have very little pressure drop. And yet, that cleans the surfaces very much. And so we had studied for small modules. These are the hollow fibers. The brine is coming normal to it, and the distilled water is flowing through the bore of the hollow fibers. And then we had a pilot plant running at United Technologies in their East Hartford, Connecticut facility. These are the modules used in pilot plant. Hot brine is coming from the top. And there is a design here that distributes the flow uniformly across the length of the hollow fibers. Each of these modules had 0.66 meters square. So we had close to 7 meters square surface area. And so I'm going to show you the results from a pilot plant which used trucked in seawater from the exhaust of a power plant at Long Island South, which had a very high calcium level in the feed seawater around 3,000 ppm. So as we started taking the water out of this seawater, calcium started precipitating. So we had precipitates all around here, and these reflect the fact that we had increased the flow velocity to see how the fluxes are affected by flow velocity, the bulk velocities. And when we had gone up to about 18-19% salt, that means we had recovered close to 80% water from that seawater. We had so much of precipitate in the whole system that we shut it down. After that, we just washed it and reused it again. Remember, this is being used in batch recirculation mode. In a real plant, you'll have continuous operation, so these precipitates would be moved away, and that requires a different type of design. I'm going to show you a few more things on this. We had cascades of such modules so that hot brine is coming in and cold distilled water is coming in, and the temperature difference in a given module would be reduced to 4 degrees centigrade. And so here it may be coming in at 90 degrees centigrade, and here it may be going out at 35 degrees centigrade, this spent brine. And then we can reheat the brine by using the distilled water which is getting heated. And that is shown in the next slide. So we have 4 such modules connected countercurrently. Hot brine is coming in to this module at the top, and cold distilled water is coming in at the bottommost module. And then the spent brine is cool down brine is going up here to a heat exchanger, which is being supplied with the hottest distilled water that is there. And we were able to show that in that setup, we could recover 5.5 to 6 pounds of water per pound of steam, so-called steam that we were supplying in terms of heat. Our simulations indicated 10, 11, 12, but we didn't use any insulation on our membrane module, so we lost a lot of heat, and we are dealing with very close temperature differences here because we wanted to see how the modules were doing. And here is an example of an actual produced water that is being treated right now by this process in Chevron's facility in California. So this is that San Ardo facility. So they have a produced water coming in, which is hot, and the oils and some of the stuff are taken out by this flotation device, and the residual oil is taken out by a walnut shell filter. And then you have the hot water coming in. So this water was sent to us in 2 drums of 55 gallons. It had about 5 to 7 ppm of oil. And we essentially replaced all of these steps, heat exchanger, cooling, deoxygen stripper, chemical reactors, flocculating clarifiers, heat exchangers, multimedia filters, softeners before it goes to a reverse osmosis unit. We replaced everything by just a membrane distillation unit, simple membrane distillation unit, fed this sample, and we didn't analyze these samples. We had to send the samples to Chevron's contractors. And our water that we were getting was about 22 total TDS. Most of it was due to carbon dioxide that is coming in because of heating from the feed side, which could be removed by stripping to some extent. And this is the direction of evolution of these modules. Those modules that we used in that pilot plant, they're very heavy, costly, had 15, 16 bolts. And it doesn't provide that much of surface area, even though it uses hollow fibers. This is a very simple design. I can lift it with no effort virtually. There are no bolts and nuts. We have only Phillips screws. And you will see what these hollow fibers paste module looks like. These are your hollow fibers. There is a central tube through which the brine is coming in, hot brine, and the brine is going cross flow across the hollow fibers and going out. The hollow fiber module design is such that you have no room for collecting any of these calcium carbonate, calcium sulfate precipitates. And we have just been recently given a patent, and it's been licensed out. Let me switch the topic. Each of these techniques take time to go and see, hopefully, some marketplace activity, but not necessarily. So let's talk about another one. There is significant amount of interest in developing a barrier or a mask that will allow moisture to go through without any problem, and yet it would block all toxic vapors and gases. And if you have a butyl rubber glove, butyl rubber blocks virtually everything. If it is a thick enough glove, it blocks everything. But it also blocks water vapor. Well, not much water vapor comes through. So there is a significant effort of using some modifications. Normally, the suits that are being used, they use a lot of activated carbon and nanometal oxides. So they're very heavy, and one would like to have rather lightweight protective garments so that they can really protect from all kinds of chemical warfare agents or other kinds of gases produced or generated by industrial accidents. So here are some examples. What people are doing is they're developing like a herd of whatever it is, a herd, a flock of birds. They're developing mixed matrix polymer composites. So they take butyl rubber or other rubbers that are somewhat more permeable to moisture and add to it metal organic framework like HQST1, which is highly likes moisture and sometimes gets dissolved in moisture and would be able to transfer the moisture through the membrane very easily. And what one finds is, yes, these devices continue the tradition of butyl rubber or nitrile rubber and block seize this one of these simulants for chemical warfare agents to a very significant extent, 1,000 minutes, 1,500 minutes, when you put high loadings of these MOFs. But the moisture vapor transpiration rate is very low, 192 grams water per meter square per day, when the minimum needed is 2,000. We now go to the other end. We have MOFs, and we use a polymer that is highly permeable to moisture, a PE or polyethylene oxide film, and it contains MOF UiO66NH2. That is a good adsorbent for many of these toxic gases. What one finds is, yes, the moisture permeability is very high. The moisture selectivity over Cs is also very high. But you cannot block the Cs for very long lengths of time, maybe at the most 100 minutes. And so it's oscillating between the two ends. Here is another attempt at with a different strategy, where they use carbon nanotube membranes as a support, as a very permeable, water vapor permeable support. And on top of the mouth of these carbon nanotubes, they synthesized a particular type of hydrogel, and that collapses as soon as it is exposed to some of these gases. But still, they can block these gases and vapors only to the tune of, say, 99%. 1% will be going through, and that 1% could be dangerous. So our strategy is quite different. We started working with graphene oxide laminates. And graphene oxide laminates, if it is perfect, it can really block these gases very effectively. But, it'll ultimately go through in practical devices. So we had exposed a graphene laminate shown right here based out of flakes of graphene oxide flakes. So it's a geolaminate. And what it does is for 15 minutes, it blocks seas completely. But after that, the rate at which it permeates is very, very low, exactly like what you saw in the previous slide of the MIT work. So what we developed is something else. We actually developed nanocrystals of MOFs, HQ, this UiO66NH2 in the pores of a porous membrane, and we put it at the bottom. Now this is our nanopack bit. So the adsorbents have come to the rescue, but supported by membranes in this structure. And these adsorbents can block high concentrations of these gases, Cs, for example, for almost 46 minutes, and then it breaks out to a very large, very significant extent. However, what we see when we have such a structure, a composite structure, DMMP is blocked completely for 7 days, and yet water vapor permeation rate is very high. Here we expose it to say 100 ppmv of ammonia containing dry nitrogen feed gas. For 2,700 minutes, there was no ammonia coming out. And we can see that graphene, ammonia would be coming out, but only at a very slow flow rate. This is about, a concentration, 4 or 5 ppm, even though feed is 100 ppmv. And the MOF field, EPTFE membrane, the nanopack bit will block it about 200 minutes, and then will come out in very high concentration. The combination of those two provides a very interesting performance, and you see that in the next slide where actual chemical warfare agents were tested, mustard and soman. And mustard, it blocked for 1,500 minutes straight out. Experiment was not continued because these are extremely costly experiments. And then soman was blocked only about 200 minutes. And it looks like our MOF was too good. We needed to have somewhat different MOF to improve this performance. And these graphene layers at the top were about 3 micrometer, and then the EPTFE is about 70, 80 micrometers. So these are very useful and potentially usable for masks and other types of barrier clothing, and we are having significant amount of work going on in that area. I'm going to talk now about, in the last few minutes, new developments in membrane solvent extraction. Now, the membrane doesn't do any separation here. There is no membrane selectivity that we can talk about. However, because it is carrying out solvent extraction and we have selectivities due to solvent extraction, the membrane properties must be good so that we don't have any problem. I'm going to bring to your attention a lot of activities going on in terms of using liquid-liquid extraction, using the hollow fiber membrane modules from bioreactors in large scale. We developed this concept many years back. The technology was developed, licensed out to Hexalenese, and those led to the development of liquid-cell modules that are being used here. But the basic concept in that technique was if you have a hydrophobic membrane, you bring an organic phase that probably wets the hydrophobic membrane pore, so you have the aqueous phase on the other side flowing at an equal or a higher, somewhat higher pressure. You cannot go to too high a pressure, then aqueous phase would be dispersed in the organic phase. If you have a hydrophilic membrane, then aqueous phase would be in the pores, and your organic phase will have to have a equal or higher pressure. And obviously, we would like to have even more comfortable processes. There are commercial units that are using those techniques. They're primarily using hydrophobic hollow fiber membranes. This one is using hydrophilic hollow fiber membranes. And so what we developed is the following. We developed Janus membranes. So we had, if you had a hydrophobic membrane, we created a hydrophilic side of the membrane. So now the hydrophilic side of the membrane will operate at whatever pressure it wants, and hydrophobic side of the membrane can operate at whatever pressure it wants, because the membrane can now handle excess pressure on both sides. We demonstrated the possibility of such operation using various types of membranes. that were appropriately modified. This is polypropylene, and these are porous nylon membranes whose surfaces were modified. Polypropylene was hydrophilized on one side, nylon was hydrophobized. With that, I'd like to conclude, and I'd like to acknowledge the considerable support from various sources and a lot of other graduate students, postdocs, and some visiting faculty members and other collaborators who have helped very much. I'd like to thank you for your kind attention, and hopefully there is time for some questions.
So any questions from the audience?
Hello.
Sir, there is one question for you.
Thank you very much, Professor Shakar. Very nice work and talk. I just wanted to quickly understand the example of the protective suit that you explained, the last but one example, where you said that the MOF, when it is crystallized inside the pores of the membrane, gave a better blockage of the gases, whereas when, if I understand correctly, when the MOF was just used in a polymer matrix, it was not so effective. And so I was just trying to understand what was the role of the crystallization inside the pores of the membrane that made it more suitable, if I understand your point correctly. Thank you.
Mixed polymer matrix membrane, MMM, has parallel pathways between the membrane and the MOF. Both are active at the same location simultaneously. And as a result, I showed you that it is very difficult to block these gases completely. Okay, you may be able to do that for one particular gas, but it would be very difficult to do it for other gases. On the other hand, the strategy that I have taken is the following. I'm saying if you have a laminated geomembrane, that has an extraordinary capacity of blocking almost all large gaseous or vapor species, except for hydrogen, helium, and a few things like that. And so the rate at which they are going to be coming out of through this laminated geomembrane would be extremely low.
Okay.
You can see it here, extremely low. And so such a low input into this nanopack bit would be very effectively taken care of because the nanopack bit has an extraordinary capacity, which is why we are able to block these gases so effectively. So here they are operating in series as opposed to a mixed matrix membrane where they are operating in parallel.
Okay.
You see, they are operating in parallel.
Yeah.
So until and unless a particular mode is really effective, there will be leakage. You won't be able to stop it. That's why the mixed matrix membranes have so far failed. There is one example where a hydrogel was prepared by Omar Farah at Northwestern University, and he had a very high concentration, 90% loading of a particular MOF. It's UIO66 and some of the others in the hydrogel in a cellulosic matrix, and it was able to block sieves for a very long length of time. But the whole point is, if you expose it to, say, chlorine or ammonia, good luck. Nothing will be stopped. They will just go through water and go right away on the other end.
Right.
So you can develop a particular solution, but conceptually you have to recognize that there are significant weaknesses of this mixed matrix concept. And that's why we went into a serial composite layer. And in fact, these masks, in general, they have multiple layers. If you look at some of these suits or other things, they have multiple layers. They have separate functions. Anyway.
Okay, thank you.
Did I make it clear?
Yeah, yeah, I understood. Yeah, so very clear now. Thank you very much. Thank you.
Sir, I have worked in the power plant, sir. I was in NTPC, and there is a lot of effluent ETP water treatment plant and storage treatment plant. Also, we are going SOX and NOx separation by the new implementation of FFG. If this type of membrane separation technology can be used in power plants, please.
You are talking about NOx in air?
NOx and SOX from the air, we implement FGD, flue gas desulfurization process presently. It is a cost-intensive process, very high cost-intensive. Is this type of membrane separation can be done there?
Right now they are not necessarily doing membrane separations as much insofar as flue gas desulfurization is concerned, although there are possibilities on that count. First of all, the flue gas that is coming out has a lot of particulate material. And on a long-term basis, if you have membrane devices, there would be these particles that be deposited and do develop a lot of fouling. That's one problem. Second problem is there are highly selective membranes that you can develop for sulfur dioxide. NOx, also there are possibilities. However, on the other side, you have to be able to take it out in some fashion. You have to develop a partial pressure driving force in some fashion. Okay? And so some of the techniques that have become successful that are being used essentially use sorbents, some calcium sorbents for taking care of sulfur dioxide and take it out. There are some scrubbing arrangements also. It can be done too. We have done some research many years back on that. But membrane devices, you have to be careful. You need gases that are very reasonably clean. And then such type of membrane devices are now being prepared, but they are being done for carbon dioxide, for removal of carbon dioxide from flue gases. There are membranes that have permeance values of as much as 2,000, 3,000 GPUs and selectivities of 140, 150 of carbon dioxide over nitrogen. And such membranes have been developed. They are being scaled up. And so you can use them, but they have to do a lot of cost-benefit analysis. And the Department of Energy here is spending in many directions. And we'll see which ones ultimately go to the marketplace, at least on the carbon dioxide front. On the sulfur dioxide, I think it's primarily calcium sorbents, and there are some scrubbing also going on. I don't know all the details.
Okay, thank you, sir, very much. Thank you very much.
So we have heard such an impressive speech from Kamlesh K. Sirkar, professor, on membrane separation processes. Thank you so much, sir. Next, I would like to call upon the next distinguished guest, Professor Shishendu De, to commence his speech. Professor Shishendu De did his BTech in 1990, MTech in 1993, and PhD in 1997 from Department of Chemical. Interest includes membrane separation, membrane casting and applications, water treatment, modeling and design, and transport in microchannel. He has authored 8 books, 16 patents, 345 publications in journals of repute, and handled more than 50 research projects and transferred 5 technologies for commercialization to 7 companies. He has guided 25 PhD and 60 plus MTech students. Professor De has been awarded several awards, including award from Indian Desalination Association 2016, Institute Chair Professorship 2020, Abdul Kalam Fellowship for Innovative Research 2017, Innovation Award from Indian Desalination Association 2016, INAE Chair Professorship 2015, Innovation Award by Ministry of Platinum Jubilee, Innovation Award by Ministry of Chemicals and Fertilizers 2015, Lockheed Martin Top 10 Innovation 2015, NASI Reliance Industries Platinum Jubilee Award 2013, INAE Silver Jubilee Award 2012, DAE SRC Young Investigator Award 2012, Shanti Swarup Bhatnagar Prize in Engineering Science by CSIR Government of India 2011, Herdelia Award 2010. He is a Fellow of Indian National Academy of Engineers, New Delhi, and the National Academy of Sciences, India, Allahabad. He is the founder of the spin-off company, Technology Separation Private Limited. Sir, could you please come on the dais and start your presentation?
Good morning, everyone. I'll be talking about sustainable and scalable indigenous technologies. I'll be taking two examples. One is the arsenic removal from the groundwater as well as the fluoride removal from groundwater. And I'll talk to you how these technologies developed in the laboratory and can be translated to the real field and for the commercialization. So we all know about the health hazard of arsenic contamination in the groundwater. Typically, the concentration of arsenic in the groundwater is in the order of 50 to 1500 microgram per liter. Overexposure of arsenic in the groundwater, it causes several discomforts, and the major outcome is that arsenocosis. It's basically a skin cancer, and what happens in the skin cancer, there are gaping wounds form on the palm and the feet, and typically the ooze, they ooze out the pus. But there is no remedy about the arsenocosis. Only the doctors prescribe to take the protein-rich diet and take the arsenic-free water. So arsenic contamination in groundwater is supposed to be second natural calamity after the Second World War. So what are the sources of arsenic in the groundwater? Generally, the arsenic is bound to the rocks wherever there are lots of iron and aluminum compounds are present, because arsenic creates a bond with the iron and aluminum compounds. Those are existing in the rock itself naturally. And because of the weathering of various rock materials, they get dissolved and the arsenic get released and come to the groundwater. Intrusion of seawater, ion exchange, and reduction of iron oxides is another mechanism that occurs in the islands like Taiwan. Presence of organic matter, the human waste as well as the animal waste. Whenever these waste, animal waste or human waste, they come with the runoff water, and whenever they face the arsenic iron and arsenic alumina bonds, these bonds break open, arsenic get released and come to the groundwater. Similar is the mechanism of the use of the phosphate fertilizer. Phosphate fertilizer, the phosphate radical is the major culprit in any fertilizer that break open the arsenic, aluminum, and arsenic ion bonds. So arsenic get released and come to the groundwater. So therefore, you can see all the river basins, which are very fertile land, so they have the arsenic contamination in the groundwater, starting from all the way north, Punjab, Haryana, UP, Bihar, Jharkhand, and West Bengal, along the Ganges, and as well as the Brahmaputra basin. So if you look into this chart, all the districts along the Ganges in West Bengal, there is huge arsenic contamination in the groundwater because of the reasons we have already talked about. And plains of Bangladesh, you can see there is full of river, and because of the arsenic contamination, all the groundwater is contaminated. Actually, this process of release of arsenic from the rocks to the groundwater is happening since millions of years. Okay, and the first arsenic contamination has been detected in West Bengal back in 1982, and in several places we have found out after that same location the arsenic contamination has increased several folds. So the major problem is that since it is happening over a long period of time, and it is unfortunate that around 1980s, 1970s, the concentration of arsenic has exceeded beyond the permissible limit, that is 10 microgram per liter. And this happens because of lots of there's lack of rainfall and the receding of the water table. So therefore, whatever arsenic has gone into the groundwater get concentrated. And during the last 50 years, the concentrated has gone. They have exceeded the permissible limit. That is 10 microgram per liter in many places of India and as well as the other places of the world. So what we have found out, we found out a natural solution of this problem. There is this lateritic soil. It's basically red earth. We call it a morum. It is generally used for the road laying purposes. So it contains lots of iron and aluminum oxides. So that's why its color is red. It's also called red earth. Now this material has a natural capability to absorb arsenic from the groundwater. So therefore, there is sufficient amount of iron and aluminum oxides that absorb arsenic. And its effectiveness can increase several folds if you can adopt a suitable treatment technique. Because it has a natural capability, but that capability itself is very low. But one can do a simple, chemical treatment. We do a, acid treatment followed by an alkali treatment. What happens in the acid treatments? The pores get opened up, and during that time, pores get opened up, as well as the surface area specific surface area increases. But at the same time, the aluminum and the iron compounds, they get dissolved with the hydrochloric acid, come out, and whenever we do the alkali treatment, they form the hydroxide, and nascent hydroxide get deposited over the material, gets absorbed inside the pores, enhancing its arsenic removal capacity several folds. Okay, so with a suitable treatment, one can increase the arsenic removal capacity of this material. So it is effective for the removal of both forms of the arsenic, arsenic 3 and arsenic 4. In a natural water, there is the ratio of arsenic 3 and 5 is in the ratio of, let's say, 70:30. Arsenic 3 is 70%. And whenever it gets oxidized to arsenic 5, then its concentration gets increased. But generally, arsenic 3 occurs around 70% and arsenic 5 around 30%. So without this particular material, without, irrespective of the pH, so it can absorb the both forms of arsenic. And we have found out there is, marginal interference from the, co-occurring ions like sulfate, chloride, magnesium, and iron. And the major important thing is that this satisfies the toxicology leaching protocol. That means whatever arsenic is bound to this material, it does not leach out under normal conditions. Even in the acidic conditions or the alkaline condition, it does not leach out, it gets bound to it. So therefore, if you just leave it, so you don't require any special treatment to dispose of this material, you just leave it for the landfilling, it does not leach out the arsenic and recontaminate the groundwater. So its removal capacity is quite high. It is around 46 milligram per gram. And this is one of the highest capacity of the arsenic for any naturally occurring material. At the same time, it contains lots of iron oxide. It's very highly capable to remove the pathogenic contaminants. It can be the filter can be scaled up to any capacity, starting from 500 to 50,000 liters per day or even higher. And there is no requirement of external power for the domestic filter. Another major striking feature of this filter is its life is pretty high. During its lifetime, 3 to 5 years, one need not to regenerate the bed. So the maintenance that basically eases out the maintenance. And so no regeneration is required during its lifetime. We have calculated the economy. It turns out to be 2 paisa per liter of the treated water. So the mechanism is basically chemisorption. So that's why it does not leach out whenever it is exposed to harsh chemical environment. So ion exchange and ligand exchange are the major mechanism for the chemisorption. Now, one can question, is it independent of the geographical location? Can I go to South India and get the lateritic soil from there, and whether that will be very good for the arsenic removal or not? So for that, we have defined a quantity called degree of lateritization. It's basically a ratio of silica divided by iron and alumina. Okay, silica, more be the silica into the material, more brittle it is. It is not desirable. On the other hand, higher is the iron and aluminum oxides present in the material, it's better for the arsenic removal. We found out that if this ratio is less than 0.4, then it's very good material for the arsenic removal. So if you get lateritic soil in any location, just do an ADX sample analysis, and if the degree of lateritization comes out to be less than 0.4, it can be used for the arsenic removal. The total arsenic adsorption capacity is 47 milligram per gram, as I said earlier. So I have given this table simply to indicate that the particle size of this material, the particle is, it's basically granular in size, 3 millimeter. So one can really, it can be used for the filter bed. If the particle, one can, if you look into the literature, there are thousands of materials which will be showing very high adsorption capacity for the arsenic and the other contaminants, but they are powdery in nature. So any powdery material that is packed in a bed, it gives the, you require a huge pressure drop to allow the flow of water through it. And second problem is that the powder material will be leaching out with the filtered water. So therefore, you require to install one nanofiltration unit, post-treatment unit, to recover those materials. So that will be expensive. So this slide gives how the disposal of the spent laterite is done. So as I said, it satisfies the TCLP protocol, and it can be exposed to any harsh pH conditions, and the adsorbed arsenic that is there bound into the material, it does not leach out of it. So this can be used as a landfilling material. It can be reused after its life will be over for the road laying purposes. Okay. So the performance curve, we have developed a master curve. So by going from the fundamentals, and we have found out, we have seen that there is an interrelation between the life of the filter, concentration of the arsenic in the feed, as well as the flow rate that you would like to have through the filter. So by looking into this curve, it's sort of a calibration curve that if you would like to have a flow rate of X, what will be the life of the filter there for a corresponding concentration of arsenic in the feed water. So some of the snapshots of the filter that we have deployed. This is the first filter deployed in one of the affected schools in Rajarhat area. This is a primary school, and its filter capacity is 500 liter per day. So in this school, the total 100 members are present at any point of time. There are around 80 students, 20 teachers, including the midday meal ladies. So they require around 250 liters water per day. There is a tap outside, so from where the villagers take the water. So this water ran for without any problem for 8 years, and by the year of 2020, when the lockdown sets in, and at the end, around 2022 or 2021 end, it was not operated during that time, and now it's still lying idle. But initially 8 years, it went perfectly, it worked perfectly all right. So in this particular figure, I've given a performance of 8 years. This is the day of one, that is the installation date. That is in October 2012, and the final this final sampling was done in 2018. Even it kept on working after that. So if you look into the black dots, the concentration of arsenic in the feed water, it varies from 50 to 200 microgram per liter. So there is a seasonal fluctuation. During the summer season, because of the lack of rain, the concentration of the arsenic in the groundwater gets increased. And in the rainy season, it gets diluted because of the rain. So, but anyway, it varies from 50 to 200 microgram per liter. That is much higher compared to the permissible limit. And these red dots are 10 microgram per liter. So they are always less than within the permissible limit. Similarly, the iron concentration. Whenever we will be doing such filter baits for the removal of the arsenic, fluoride, or anything, one has to install an iron removal unit at the upfront, because if you do not do that, over a longer period of time, the iron gets deposited in the actual filter bed, and the whole filter bed gets choked. Okay. So at the same time, the iron concentration, which is around 5 to 25 ppm, it can be reduced to less than 0.3 ppm. That is the permissible limit. The coliform count, so actually WHO limit is the coliform count in a drinking water should be less than 10 CFU per ml. So if you can see, you can survey the market, there are lots of filters available which will be saying that they can remove more than 90% of the coliform. But generally the coliform count in the feed water is around 10 to the 6 CFU per ml to 10 to the 5. So 90% removal means there's still remaining 100 CFU per ml, which is not permissible. But actually this filter, it reduces its concentration to below detection level. So several domestic filters of 120 liters per day capacity have been deployed in several affected areas of different districts. Some of the domestic filters, these are domestic filters. There is a filter body. It's a column filled up with the material, and there is a bucket on the top. They do first give a certain amount of alum so that the iron get deposited, and from the top of it, a tap is taken, and there is a valve here, and that controls the flow rate. Now water is allowed to flow through the filter and gets collected in the bottom. So it's a very simple device. So this is the performance of a domestic filters. This is 3 years performance. Okay, now since the flow rate is less in this case and the maintenance is better, the performance of the filter is much better here. You can see the black dots, the feed concentration is varying around 100 to 300 microgram per liter. Sometimes, in some cases, we have we have seen that the same well gave there is a shoot up of the concentration sometimes. So concentration of the filtrate in most of the cases, in all the cases, is less than 10 microgram per liter. Same is the case of the iron. Another community scale filter, 1500 liter per day, that has been deployed in one of the girls' school in one of the affected areas. So here the inlet concentration of arsenic is 300 microgram per liter, and the filtrate is much less than 10, same as the iron. Another has been deployed in 2024 in Rotua 2 block in Malda district. So after that, these technology has been commercialized and into 3 companies. And these are the very big filters they have come up. These are really community scale filters of 2 meter cube per hour capacity. More than 250 such filters by now they have been deployed in various places of West Bengal, Assam, and Jharkhand. And it has been approved by the Arsenic Task Force Government of West Bengal. And this technology has been included in one of the possible technologies in the tender of Government of West Bengal. So, since these community-based filters, they are basically expensive filters for the vendors who have deployed it. So there is a payment against performance. They said PAPA mode, so payments against performance. So this performance of these filters have been checked by the PHE labs of different districts of Government of West Bengal. And when they find out that the performance is satisfactory, then only partial payment is released. So it's not that the filtered water is taken to the IIT and then checked. It is basically being monitored by the public health and engineering labs in different districts. So what are the elements of the innovations in this particular technology? First of all, it is a low-cost material without compromising of the quality. Since the starting material is a naturally occurring material, the expense is less. On the other hand, the nearest competitor to this technology is activated alumina, which is a synthetic material. And the commercial price of this material is almost half compared to the activated alumina. Design is the next innovation. It has a long life, 5 to 7 years without any hassle, without any problem, and without any regeneration. That is the major thing. So therefore, that makes out the maintenance easy. At the same time, we are able to remove iron, bacteria, and arsenic. So this is a value addition. So this is the third innovation. The fourth one is no regeneration of the material. So we don't require any chemical regeneration that is quite frequent in other materials. And that will, the arsenic that is coming out of the material can go into the groundwater and recontaminate it. That is not there. And the disposal is very easy because it satisfies the TCLP protocol. It can be after its life will be over, after 5 years or 7 years, it can be used for the road laying purposes. So this is the status of these technologies. It is been listed as one of the top 100 innovations in India in 2022 by the Innovator Association of India. It has won several awards, including the Hindustan Door Oliver Prize by IICHE in 2019. This is a finalist of the Dhirubhai Ambani Prize of ICEIS UK in 2016. Innovation Award from the Indian Desalination Association. This has been shortlisted as one of the top 4 technologies by Reed Elsevier Environmental Challenge in 2015. And it has been approved by Arsenic Task Force, Government of West Bengal, as well as the Department of Science and Technology and Ministry of Drinking Water and Sanitation. This technology is transferred to 3 companies for the commercialization. And currently, more than 300 community scale filters of capacity 2 meter cube per hour to 5 meter cube per hour is there in different locations of West Bengal, Assam, Bihar, and Jharkhand. So I'll come to the next case study, that is the fluoride removal from using the aluminum substituted hydroxyapatite incorporated wood charcoal. Like arsenic, the major difference of arsenic and fluoride is overexposure. Fluoride is required to the human health to some extent, but overexposure of fluoride concentration will lead to a disease called fluorosis. So there are 2 types of fluorosis. One is the dental fluorosis, another is the skeletal fluorosis. So over intake of the fluoride content in the drinking water, it basically weakens the bone. So the teeth get disfigured, the bones get weakened, and it leads to the early onset of osteoporosis. So that is the problem of the fluorosis. And like arsenic, fluoride is happening in the rock in the form of hydroxyapatite. So it's basically calcium rock, okay? Now, there are more number of states in India that has been suffering from the fluoride contamination in the groundwater, like in Andhra Pradesh, Telangana, Karnataka, Gujarat, Rajasthan, Bihar, UP, parts of Haryana and Punjab, and even if you go to Tripura and Assam, there are lots of fluoride contamination in the groundwater. So what we did, first of all, we started to look into by following the success of the arsenic removal media, we started to look into any naturally occurring material is available or material is available which will be removing the fluoride from the groundwater. So we have found out that if you take bone meal, so any bone animal bone contains calcium. So calcium is a very good material to absorb fluoride to form the calcium fluoride. So we started with the bone meal, which is basically a fertilizer. Okay. So then we burnt it and formed into carbon, and that carbon worked pretty well for the fluoride removal. Ultimately, we presented the technology in front of the Fluoride Task Force Government of West Bengal. They are very happy and so to look into its results over a couple of years. But ultimately, they rejected it. Why it was rejected? Because they said that since the starting material is basically a bone meal, it's an animal origin, that may lead to communal violence. Okay, so they just instructed us, Professor, they just look into some other way to handle this problem, not any animal origin. So then we look into the wood charcoal, and ultimately we tried to mimic the hydroxyapatite phase, which is basically the material that is there inside the rock to arrest the fluoride. What we did, we took the commercial wood charcoal, which is quite porous. Porous means surface area is around 500 to 700 meters square per gram. That is available commercially, starting from the wood origin. Okay, so then we developed this hydroxyapatite phase in situ inside the porous matrix of the wood charcoal. So now this material is already granular in size, around 2 to 3 millimeter. So there is absolutely no problem as a packing material in an adsorption bed. So we developed it, and this hydroxyapatite phase has been grown in situ inside the porous matrix of the carbon, and some of the calcium centers have been replaced by the aluminum, because aluminum will be arresting 3 fluoride atoms. On the other hand, the calcium will be arresting 2. So therefore, the idea is if we substitute the calcium partially by aluminum, its capacity will be enhanced several folds. So this technology is also being transferred, and this is the place of where they are producing it commercially. Now they are producing around 150 kg per batch, and it is being scaled up. By now it has been scaled up to 500 kg per batch. So I have given this table to show that the size is really granular in nature, and it has a high specific surface area, as well as if you look into the fluoride removal adsorption capacity, it is 105 milligram per gram. More than 100 milligram per gram, that is probably one of the material that has been reported maximum capacity, which is in the granular form. So for that, I have given a table. So all these are basically the granular material. See, if you look into the activated alumina, they still use activated alumina for the fluoride removal as well as the arsenic removal. The capacity is 25 milligram per gram. And all these are basically the granular materials. Among the granular material, if you just look into this has several times compared to the capacity compared to the other materials. So with this material, we developed a filter, and this has been commercialized last year only. And this whole development has been done during the lockdown period only. This is the uptake mechanism. It's basically ion exchange and the surface adsorption. So there are calcium and the aluminum centers where there is adsorption taking place, as well as there are the these hydroxyl radicals are being ion exchanged with the fluoride. So what is the disposal mechanism? So in this case, the disposal of the spent adsorbent is like this. So it is it can be used as a fuel. So it has a strong calorific value. The calorific value of coal and this hydroxyapatite aluminum hydroxide. So it's basically if we mix up with the coal, then fire it, so it can be used as a it can be reused for as a fuel. And now, if you look into this, the 97% of fluoride that is there inside the ash and 3% is in the gaseous form. So the possibility of the fluoride contamination from the gas phase is minimized. So that is not an issue at all, 3% in the gas phase. 97% is occurring in the ash. But even if we have studied how much leaching is there from the ash, that we have found out in most of the cases it is less than 1 milligram per liter. So even if the permissible limit of the fluoride in the groundwater is 1.5 milligram per liter, in most of the cases it happens in the concentration range around 2 to, sometimes it is as high as 10 to 15 milligram per liter. The difference between the arsenic and fluoride has to be noted. The arsenic occurs in microgram per liter level, fluoride occurs in milligram per liter level, okay, 1,000 times. So we have developed the integrated filter and deployed this prototype in several places of capacity 80 liter per day. It's a household filter. So we have also seen that there is no leaching of aluminum and calcium ions from the material over long-term use. And this is one of the filter performance that I've shown here. So this is deployed in one of the houses. There the fluoride contamination is there in the groundwater. This is the kid in the house. So this child is affected by the dental fluorosis. So if you look into the concentration, it varies from 2 to 2.5, around 2.5 sometimes. So and the concentration of the fluoride in the filtrate is always less than 1.5 milligram per liter. So these almost 1 year performance. In fact, this filter has been designed such that this media has to be changed every 1 year. Whereas any activated laterite, activated alumina-based media, you have to regenerate the media every week. That is why alkali solution. So again, this is a domestic filter performance that has been deployed in another place in Jamda in Bankura district, where the concentration is a bit little higher, 2.5 to 3.5, and the concentration is always less than permissible level for the last 1 year. This is one of the community-based filter that has been deployed in one of the primary school in Bankura. But here, the concentration is always around 1.5 milligram per liter. The technology has been transferred, commercialized. The community-based filters have been deployed in 12 places in West Bengal, 6 in Purulia district and 6 in Bankura. And if you look into the concentration, it varies from 1.6 to 2.8 milligram per liter in different places. And in some places of Bankura that I have not shown here, the concentration is as high as 9 milligram per liter. And this is the filtered concentration after 8 months. These have been deployed around 8 months back. And if you look into the concentration, they are much, much less than whatever is permissible limit. So if you look into the manufacturing cost of the household filters, total manufacturing cost is around 1,800. But if you just make it double as a retailer price, it may be around 3,000. And cost of filtered water is 2 paisa per liter. So one can take care that every year the material has been replaced. Now, if you can just compare with the filters, those are available in the market. So if you look into the filters, those are available in the market for the fluoride removal of the same capacity, they are varying from 15,000 to 40,000. And this filter can be sold at a price of 3,000 to 4,000 rupees only. So what is the status of these technologies? This technology is approved by the Fluoride Task Force, Government of West Bengal, as well as the Department of Science and Technology. This technology is transferred for commercialization to one company till now. And what are the elements of the innovation? So there is in situ growth of hydroxyapatite phase, which is mainly responsible for the absorption of the fluoride in the porous carbon matrix. And we substitute some calcium by alumina so that the capacity gets enhanced several folds. Granular in size of the adsorbent so that it can be used as a packing material of a continuous flow packed bed. You can remove the iron, fluoride, and bacteria at a time. So the outcome of this work is basically a social stigma. We started to work with the bone charcoal, and finally we landed up with this material. So how the social outlook and the government influence can change the course of a research, that is one of the examples. So now I have a timeline of taking technology to the field. For the arsenic removal technology, we started to work in 2004, and we got support from DST by showing preliminary results in 2007. The first domestic filter was deployed in 2011, and we got the approval on the same year. And the community-based filter is designed and deployed for the first time in 2012. And in 2015, after a couple of years, field trial and results we have shown, then the first technology transfer occurred in 2015. Second occurred in 2017. We got the approval from Ministry of Drinking Water and Sanitation by showing the already deployed filters. And the third technology transfer occurred in 2019. So it's basically the continuous and sustained effort from 2004 to 2019, 15 years effort to bring up a technology from the laboratory to the field scale. And only in last year, this has been included in the top 100 innovation in India by Innovators Association of India. Similarly, the fluoride removal technology, I tried to chalk down a timeline. We started working on using animal bone meal in 2013. We got support from DST showing the preliminary results with this material only. The first domestic filter was deployed in 2015, and we made a presentation in front of our fluoride task force, Government of West Bengal, in 2018 by showing the results from the deployed filters. In 2019, the fluoride task force rejected the technology because of the reasons I have already talked about. Then we started working on aluminum hydroxyapatite carbon, and the material was developed in 2021 only, and the domestic filters were deployed. 2022, the technology was transferred, and on the same year, last year only, the fluoride task force, Government of West Bengal, they have accepted this technology and approved this one. And by now, there are 12 community-based filters of 2 meter cube per hour capacity have been deployed in different locations of Purulia and Bankura. So I just jotted down some of the steps for successful development of a technology. For any technology development, the starting material should be a commercial material. So you should not work with the any analytical grade material, because if you start preparation of a material commercial in a big scale, any analytical grade material will be starting material, raw materials will be expensive. So commercially available raw materials, easy and cost-effective, scalable method of preparation. The preparation method is very, very important. You should not deal with any sophisticated machine or high-speed centrifuge. Those are working pretty well in the laboratory scale. But if you go to the real plant scale, all these machines will not be working. Suppose you would like to have a freeze dryer. Can you prepare a 1 ton of material per day using a freeze dryer? It is not possible. Simply not possible. Okay, so you can prepare a material of 5 grams in the laboratory using a freeze dryer, but not 1 ton per day. So that is the objective. So you should not use any unscalable method or very expensive material to prepare the material in the laboratory scale. In the laboratory scale, you have prepared it fine, but one should look into that how it can be commercialized by avoiding the expensive equipment. Outreach capability of the technology, that means it should be affordable to the end users. Ultimately, the technology will be used by the end users. If you have developed a rocket technology, but that is very, very expensive, then it's of no use. So third point is the scalability. Whether it can be really scalable. The filter that I have developed, it is 80 liter, 100 liter per day. Can it be scalable to 10 meter cube per day? Yes, it is possible. Then, okay, fine. So scalability is another issue. Then sustained and relentless. If you look into the timeline, it takes more than 10 years minimum to develop a technology and bring it to the level to the commercialization. So I think there are it's the effort of several PhD students who have started the material, developed it, and the baton has been changed and transferred to the next batch of PhD students who have developed it further, and finally it came to that level. So a sustained effort is required, and this point is very important. You should have approval of the regulatory bodies. Okay, otherwise whether it's a medical device, whether it's a other devices, but there are regulatory bodies. So you have to give a presentation in front of the regulatory bodies. They look into the pros and cons, performance, look into the performance in the real field, and then they will give the approval. That is very important. Unless and until they give approval, it cannot be used in commercial level. Nobody will be interested into it. Coordination of researchers, government bodies, local authorities, and end users. That is very, very important. This coordination is very, very important, because we do something, we develop something based on our interest and our method, but it may not be very suitable for the stakeholders. Okay, so suppose you will be developing a filter which will be removing arsenic or the fluoride to the finest extent, but it contains the other materials, other contaminants which are not, suppose the iron level is higher than whatever is accepted. So that is not acceptable. So coordination of researchers, the goals of the final product, the government regulations, local authorities, panchayat level, and the end users, whether the operation and the maintenance is easier or not. So that is you should get the continuous feedback from the end user. So keep on. So you cannot hit at the first instance. So there will be an exchange of opinion, and the shortcomings will be pointed out by the end users. Then you have to improve it upon. Okay, so be truthful to work and output. So that is very, very important. Suppose whenever I have probably given at least 5 presentations in front of the Arsenic Task Force, Government of West Bengal, at least 4 to 5 to Fluoride Task Force. I've given 3 presentations in front of the Jal Sampad Mantak, that is the Ministry of Drinking Water and Sanitation. So that is very important. So you should be truthful. That means, for example, in order to get the approval from Central Ministry, what they said, they have listened to my presentation, they said, fine, no problem. And they have employed NIRI to check whether whatever I am claiming that is correct or not. So they have taken the list of different locations where the big filters, community size filters have been deployed, and they employed NIRI and sent and picked up any such filters from any locations, not one, maybe 3 or 4 of them. And they sent the team of NIRI and looked into took up the samples, and it has been sent to NIRI Nagpur for the analysis, not in NIRI Kolkata. So then it was satisfactory and the approval was given. So government approval is very, very important. Once you show the government approval, then any vendor will come up or entrepreneur will come up to commercialize the technology. Okay. So if I develop something, suppose if I develop 2 and I say, no, I have developed 10, that is ultimately it will fire back. So you should be very, very truthful to work and output. And of course, there is no substitute of hard work. So with simple intelligence, you can reach around 70% of whatever is aiming for. But with the hard work, you can make up the rest 30%. Thank you very much. If you have any queries. Yeah.
Sir, any questions out there for sir?
Yeah, Professor Chitantu, it was wonderful getting to know that there are simple technologies for overcapping fluoride and arsenic removal. But my question is that suppose fluoride is not a problem or arsenic is not a problem, possibly confined to just West Bengal. So there must be problems in other states also. Yeah. There is, I guess. Huh? So in other states, this soil is not available. So the essential of this soil, the essential components of the soil I felt was iron and alumina, right? Yeah. So my question is that whether just iron in its original form would be suitable in those states where this soil is not found?
Actually, any synthetic material will be expensive compared to whatever we have done, because our source material is absolutely naturally occurring. Now the point is whether the laterite that is available in the other states, whether they're suitable or not for the arsenic removal. So we have shown that there is a degree of lateritization. We can check out the soil and we can find out what is the degree of lateritization. If it is less than 0.4, it is fine. It can be used for the arsenic removal. Otherwise, around West Bengal, Jharkhand, this area, this lateritic soil is very good, and there is a vast reserve of this material. So already there are 3 companies who are commercially producing it, probably in order of 3 to 4 tons per week. So they will be able to supply this material. As far as the fluoride is concerned, the material for the removal of the fluoride is not a naturally occurring material. It's a synthetic material with the commercial grade chemicals. Those are available in market. So it can the production unit can be set up at any place.
Thank you.
Thank you, Professor, for your excellent presentation. Especially, you had presented the technology scaling up. Professor, would you please be kind enough to explain the ultimate disposal of arsenic? I mean, initially it was in groundwater. Later, after your filtration, you had presented that 6 or 7 years is longevity your filter you had developed. So my question is, what is the ultimate disposal of the arsenic? Initially it is in groundwater, now it is in ground or air. The toxicity of arsenic is still there.
Right.
Yes, what will be the
Fate
ultimate
of the-
disposal
yeah.
of?
Okay. So actually this material that we have used, we have prepared from the lateritic soil. This laterite, it's basically known as moram. So it is, conventionally it is used for the laying the roads. They give the first layer of laterite. Then they give the other materials, sand. Then they put the asphalt layer on it. Now this material, it has satisfied that TCLP protocol. That is a standard international protocol. It is a toxicology leaching protocol. If the material is satisfied by that protocol, then that indicates whatever the arsenic or heavy metal that has been attached to the material, it does not leach out. It is very safe as at least the ground filling material. So our material, it absorbs arsenic by strong chemisorption, and we have proved that it satisfies the TCLP protocol. So therefore, the arsenic that has been bound to it, they do not leach out. Okay. So again, this material, after 5 to 7 years of its life, the material can be used as a road laying purposes without any possibility of leaching out of arsenic and recontamination of the groundwater. Okay. For the fluoride removal media, it can be used as a fuel.
Okay. Thank you very much, Professor.
Very nice, very commendable deployment. So, of course, you showed very high adsorption capacity. I was just curious about the kinetics, that is, what is the rate it is picking up. Especially, I thought you showed a fluctuating include concentration of the arsenic example because of summer or rainy season variation. So, intuitively, it may be possible that when the external concentration, or whether it is arsenic or fluoride, has gone low, it may leach back if the rate of release is sufficiently high. And does that happen? I mean, over a short time period. Yeah. So such fluctuations can, that will be connected to, I was thinking, which you partially answered, that whether it is chemisorbed or physisorbed, yeah, right. And you must have measured the adsorption, yes, energy, and so would you just correlate the kinetic time scale with the adsorption energy and throw some light on it? Yeah. Thank you very much.
So these, we have already looked into the kinetics. I didn't show it here. For the arsenic removal media, the kinetics is pretty fast. Within half an hour, even it can, the concentration of 400 to 500 microgram per liter level will go down below 20. On the other hand, in case of fluoride, we have looked into the adsorption energy, and we have concluded that the chemisorption is the main mechanism of the adsorption in case of arsenic. In case of fluoride, it is physisorption. So fluoride, the kinetics is quite a bit low, slow compared to the arsenic, but these parameters for the kinetics as well as the isotherm parameters, that whatever you have developed, those will be used to design the filters by putting back all those two partial differential equations to scale up the filters. So therefore, being a chemical engineer, so we can always design a filter and pack the filter with the amount of sufficient amount of material so that its life will be fixed, subject to the flow rate and the concentration in the feed. So we can always design a filter and pack a media, pack the X amount of material inside it, ensuring that its life will be met for 1 year for fluoride and let's say 3 years for arsenic.
Yeah, that is fine. My point was over a short time window, when there is external fluctuation in the concentration, let's say from summer to rainy season,
yes,
5 months, there will be a desorption rate.
Right.
Because the surrounding concentration has gone down.
Right.
Does it pose any short-term problem?
It does not, because I showed the concentration of the arsenic in the filtrate over the period of 6 years. There is a fluctuation. You are absolutely right. Because of the seasonal fluctuation of the feed, there is a variation of concentration of the arsenic in the filtrate as well. But the filter is designed in such a way, concentration is always kept less than 10 microgram per liter.
Sir, one thing I want to, what you have told that moram is a red color type of substance, I think.
It is red earth.
red earth, then what may be the chemical formula for the laterite, and is it available in the market, and what will be the cost? Thank you.
This lateritic soil is available in abundance in western part. It's a western part of West Bengal as well as Bihar and Jharkhand.
Now, what type of the chemical
composition? It contains lots of iron oxides and aluminum oxides, geothite, and there are other forms like, I did not show the XRD report. These are the various forms of iron oxides and aluminum oxides are present. Okay, hydroxide, oxide, and all these things are present. Now, there is no single chemical formula of this material. It's a congregation of the different materials. So it's a naturally occurring soil. As far as there is a chemical treatment we give to this material so that its arsenic removal capacity enhances several folds. Now, the commercial production cost of this material is around 100 rupees per kg, including all the utility costs, water, electricity, etc. It costs around 100 rupees per kg. Compared to this laterite, we have the activated alumina as an alternative, which is the nearest competitor to this material. It costs around 210 rupees per kg before lockdown. Oh. So it must be around 250 rupees per kg by now. So its cost is half that way, and its capacity is probably the activated alumina. Its cost is around 10 milligram per gram, and this material has a capacity around 50 milligram per gram. 47, I said, 50 around. It's 5 times. So with the less amount of media, one can run a filter, one can design a filter so that it can run several months without any regeneration.
Okay, so thank you very much for that.
Thank you very much for this development. I congratulate you. I have just a basic question that whether you have performed any life cycle assessment of the entire process, starting from the development of the adsorbent and finished product. So what is the environmental impact assessment of the process?
Yeah, so during the preparation of the acid and alkali treatment of this material, the material that is formed that may impact the environment is basically the water that is coming out from the treatment process, and it contains sodium chloride, because there is acid treatment followed by the alkali treatment. Sodium chloride at pH 7. So there is no pH fluctuation of the disposal of the liquid stream whenever we are producing this material. It contains TDS, and we have already seen that TDS is less than 200 milligram per liter. So also it does not pose any threat to the environment. Production of the material, starting from the raw material, a particular batch, it requires 2 days time, including all the treatment procedures. Then you put into the oven or sun dry it and make it dry. That is as far as the material preparation is concerned. I'm talking about a production scale of around 500 kg per day. Okay, so with one of the startup is having that capacity. Regarding the filter, as I said, that filter life is around minimum 3 years. Maximum it can go to 5 years, depending on the concentration of the arsenic in the feed. So you do not require any regeneration of the media during its lifetime. So its maintenance cost will be much simpler. There is absolutely no maintenance cost. Just put the filter, keep it in operation, and start doing the filtration. That's all. And there is no maintenance required, almost no maintenance required. Only there is an iron removal unit that has to be put in the upfront, and iron is removed by the manganese dioxide coated sand. That is a standard technique in a water treatment field. Okay, and one has to have a monthly regeneration of the iron removal unit, not the arsenic removal unit. So that is the life cycle of the filter. Yes.
First is the drinking water that we are having through this RO. Does it have arsenic? This is question 1. And question 2 is that will it be better to use some size exclusion? I mean, of course, you are doing the cost issue related to this laterite and all. But then you are also using a chemical technique. It is getting adsorbed, and then, your regeneration time is becoming less. So is it
No, I'm not regenerating it at all.
So it's a use and throw, right?
It is use and throw.
So is it better to use a kind of size exclusion to remove arsenic? I mean, fundamentally...
size exclusion has to be done only by RO. There is absolutely no other way to remove arsenic by size exclusion or even fluoride by size exclusion. Only RO is the solution. But there are two forms of arsenic, arsenic 3 and arsenic 5. Arsenic 5 bigger in size, that is excluded easily compared to arsenic 3. There is a partial retention of arsenic 3 even in RO. And in the fresh groundwater, the 70% of arsenic comes from arsenic 3, rest 30% from arsenic 5. So even in fresh, if you do the reverse osmosis in a fresh groundwater, there is a partial size exclusion of arsenic, not completely. The places where the concentration is as high as 500 ppb or even 1500 ppb in Bangladesh, RO will not work. Absolutely it will not work. On the other hand, in the villages where most of the people are getting affected, there you cannot think of employing RO.
Say whatever AquaGuard and all we are using.
AquaGuard does not work anything. AquaGuard, if you just open up the AquaGuard filter, there are carbon candle filters. There is nothing there. In RO, there is a removal of the salt TDS, and the Supreme Court ruled out that if the concentration is less than 500 ppm, there is RO use is banned. It should not be used. It can only be used if the concentration is exceeding 500 ppm. Even if you use RO or Kent RO in some areas where the TDS is less than 500 ppm, I think there is a mechanism to adjust the tuning of the salt, TDS. TDS tuner is there. What TDS tuner does, so basically RO removes 99% of the TDS, okay? The concentration goes below to 40 ppm or 50 ppm level. If you start drinking that water, you'll be falling sick because of the concentration gradient, the salt from your body will be coming out. So you'll be, then there will be a desalination problem in the physiological system itself. So they use the TDS tuner in the Kent RO. So they artificially add TDS to the system, so that is the thing. And the Kent RO thing is the capacity is 6,000 liter. That is the lifetime of the membrane, 6,000 liter. After 6,000 liter you have processed, then you have to replace it. And cost difference is order of magnitude.
Professor, I have another question. You see, you had presented a lot of many things for preparation of your ion exchange material or else.
So there is a reason for doing that, because any technology will be successful if the material preparation is low cost, yes, and the application is also low cost, okay, and easy to maintain. Okay. So if you prepare a very high cost material, that will not be commercialized.
Professor, I would like to know, can you replace this your technology with electrocoagulation? You are talking about size is a related issue. Electrocoagulation, you can use 2 electrodes, and the cost of the electricity, maybe 2 or 3 municipalities sodium light is quite enough to remove the your impurities within 10 seconds. So you are doing many things, many technology, just electricity use, it will coagulate, and
Excuse
later
me, sir.
you can discard.
Can I cut you here? Actually, he's the session chair for another building, in Nechal Roy building. Okay. So you can discuss it while having
Professor,
high tea
I will discuss
or,
later.
I
or
can
in
give a
lunch
short answer
session.
for your question. Yes, okay. Electrocoagulation you have checked.
Yes.
Electrocoagulation is not suitable for having a community scale filter, which is basically 2 meter, minimum is 2 meter cube per hour, running for 5 hours a day, 10 meter cube per day. That capacity cannot be handled by electrocoagulation. Okay, number one. Number two is, if you even put the electrodes to treat that capacity, first of all, you require very huge area of the electrodes. Okay. And the loss of electrode is so fast, and the consumption of the electricity is also not coming out to be economical. We have also checked the whether the electrocoagulation is viable to this process or not. It is not viable.
Okay, thank you. Thank you very much, Professor.
Actually, the government aim is to go for the community scale filters. Now, even they do not want to deploy the domestic scale filters. They want to deploy filters which will be capacity 10 meter cube per hour, 2 meter cube per hour, 5 meter cube per hour. Even in one of the locations where our material is being used, the capacity is 80 meter cube per hour. That will be catering to cluster of villages.
Thank you, sir, for your wonderful discussion that has enriched us on the field of fluoride and arsenic removal. I would ask Professor Abhijit Bhawal, Department of Chemical Engineering, Jadavpur University, to felicitate Professor Shishendra today. Next, I would like to ask our distinguished speaker, Professor Gautam Deo, to begin his session. Professor Gautam Deo joined the Chemical Engineering Department at the Indian Institute of Technology, Kanpur in July 1996. He received his B.Tech from Indian Institute of Technology, Kharagpur in 1985, MS from University of Iowa in 1988, and PhD from Lehigh University 1992. His main area of research are in catalysis and reaction engineering, while specific interest in supported metals and metal oxide catalysts and their promotion. He has also served in several administrative roles, such as member of the Board of Governors, the head of chemical engineering, a short stint at the Dean of School Affairs, and head of counseling service, to name a few. Sir, please come to the podium and start your session. Thank you. You will be needing a microphone.
Is it required for the live streaming?
Yes, sir, it will be required. Your microphone is here, sir.
That's not come up as yet. One second. Ask me. Now ask. I guess I'm audible. I would be audible without this microphone also, but since it is getting live streamed, I think that is necessary. So what I'll try to do is give you a snapshot in terms of what we have been doing in the IIT Kanpur and the Chemical Engineering Department. And considering the fact that this is a year of celebrating, or perhaps a bit delayed celebration of the Chemical Engineering Department at Jadavpur University, what I thought it best actually to give you a snapshot as to how Jadavpur University itself, the Chemical Engineering Department, has helped me in the last quarter of a century of my journey in terms of research and catalysis. So what I'll be talking about is this conversion of carbon dioxide, which seems to be a catch nowadays. It is not necessarily meant to be a catchphrase. We are trying to see if we can actually convert this CO2, which can be produced at different sources, and make them into some value-added products. And then to do that, over the years, I have had the support of a lot of friends from Jadavpur University, and a lot of brilliant students also from Jadavpur University. And out here is basically, I knew that this would happen. Out here is basically a few of them. All of these four are people who have been a student out here, and I thank you for training them well. We have out here Professor Deva Prasad C. He's right now in IIT Hyderabad. He's a faculty member out there. Professor Taraknath Das, who is right now a faculty at IIT Roorkee. Siddharth Sengupta, professor, he's at IIT ISM Dhanbad. And Professor Kaustav Ray, he was there in the audience somewhere. He is right now a faculty member at IIT Kharagpur. So all of these people, I mean, of course, I've had some MTech students, out of which Shomik has been in General Electric for quite some time. So all of them have actually contributed in terms of my journey for the last several years in chemical engineering department. And well, whatever I'm going to present is basically a bit of the stories in which they developed, and later on people have carried on with that ideas. So all of us know that there is this close linkage between the temperature rise and the CO2 in the atmosphere, and this graph is essentially showing that. Out here in this axis you can see the atmospheric CO2 in terms of ppm, and you can see that this red line is essentially the one which is showing that the CO2 is increasing. And of course, doing the rescaling, if you look in terms of the temperature anomaly, which is there, you can see that there is a very close correlation between this temperature rise and the CO2. I will not be a proponent of saying that, oh, it's a bad thing. There are correlations, CO2 increasing, temperature rise, seawater level increasing, and so on and so forth. The problem to me as a chemical engineer that CO2 is increasing, and is there something one can do about it? And there are. This is some of the numbers, some of the statistics. You have about 37 gigatons of CO2 being produced for energy requirements, just for energy. There are other ways in which where you can produce CO2, especially in cement, for example. And this is in 2021, and we only consume about 230 million tons of it. And you can see the largest consumer of CO2 is in the fertilizer manufacture, which is essentially urea. And you can see a lot of recent development in terms of this enhanced oil recovery. You use about 34% of the CO2. Balance small amounts, but then there are a lot of carbonated drinks which actually, where you can use this compressed CO2 for beverages. And the HeadCat lab at IIT, this is the lab which I happen to be a part of, we look at three CO2 conversion reactions. They are the methane reforming. So we're taking methane and trying to reform it just like you do in the industrial plant to produce hydrogen. Out here we're using CO2 and methane and producing syngas and hydrogen as well. And we have then tried to modify it, and then consequently I've said that there is the methane reforming and the other avatars. There is like a part 1, part 2, and part 3, and so on and so forth, where we can take this methane and try to extract the hydrogen from many different forms, not only by using steam, but also by using by CO2 and then modify it based on a requirement. The other reaction is the CO2 methanation, which is in itself a very interesting reaction, and I'll try to impress upon you why it has become, why it is to me an interesting reaction in the recent past. And then there is the CO2-assisted dehydrogenation of propane, which is something which only recently people are trying to do in terms of seeing that if this is a feasible reaction, which is going to be economically viable to do in terms of the industry. Okay, so in all of this, our catalysts play a very important role. And while we're doing any of these different processes, we are looking at the catalyst design. And when we're designing this catalyst, we are essentially in all of them, and all of the people who have shown you in the photograph have made the catalyst. They use it for whatever they made. They try to ensure that they can characterize instead of understanding what kind of catalyst they have made. They do some theoretical analysis in terms of DFT and thermodynamics, and then they study the reactions. And out here, you have got the reforming reactions or the methanation reaction, or in terms of the propane, thank you, propane dehydrogenation reaction. Okay, so while doing that, this is essentially what is shown out here in terms of a bit more detail. Yeah, they're making the catalyst out here. This is, of course, making the catalyst in terms of gram amounts, not tons, but gram amounts, so that they can test in terms of the reproducibility, the characterization in terms of what they have made. They characterize it properly. Out here I'm showing in terms of metal characterization, in terms of using characterization techniques like TPR or particle size distribution. And after make all of this in terms of making and characterizing, they have actually an idea of what kind of material they have made in terms of this metal which is there for this metal catalyst, which is there on using a catalyst A, and then what kind of size of these metals which are there in this catalyst B. And then they can use it in terms of reaction to understand why catalyst A is different from catalyst B. It may be better or worse, but at least they have now a reason in terms of the characterization of this catalyst as why they can be different. And helpfully that knowledge can be used in terms of improving what the catalyst is, or what the catalysts they have made in terms of the reaction. Okay, so the first reaction which I'll talk about is the dry reforming of methane, and then that's Professor Siddharth Sengupta. And I still remember this is the time when I was the head of the department at Kanpur, and I was obviously busy in this administrative role. He perhaps felt a bit neglected. So he has been going on his own, looking, which I guess the training which he got out here, looking around in the lab and trying to see what would he like to do. And he said that, sir, we have got methane, we have got CO2, why can't we do CO2 dry reforming? And that was actually the buzzword in those kind of years. And he was responsible actually to set the whole thing up in terms of the research in this particular area. And if you can see this particular reaction, we are taking methane and trying to reform it, essentially trying to take out the hydrogen from it. And along the way, we're using CO2. And this is a reaction which is very similar to the steam reforming reaction, which is ordinarily used in the industry, for example, to produce hydrogen, which can be used in your urea manufacture or ammonia synthesis, and then urea. And instead of using moisture, we are using CO2. Instead of using steam, we're using CO2, and we're doing this particular reaction. And along with it, as you'll see, this reaction of the reverse water gas shift reaction, where this hydrogen is going to then react with the reactant, and your CO and water is formed, which is, if you go from the right to the left, is the water gas shift reaction, and out here, actually because of the abundance and the temperature conditions, it's going to go from the left to the right, which is then the reverse water gas shift reaction. But the bad thing about this particular reaction, which is not as strongly implemented in terms of the steam reforming reaction, is because the number of carbon atoms out here are much larger. Right? In the methane, you just have one carbon atom. When you're putting CO2, you're having those two carbon atoms. And then the propensity of actually depositing carbon, and that happens essentially in terms of the cracking reaction, is much more. And that becomes a bad thing. The bad thing is the fact that this carbon then can give rise to deactivation. So the conditions which are used for the dry reforming is much more stringent compared to the steam reforming reaction in terms of the temperature and pressure and the conditions which are used. The good thing about this dry reforming reaction, since it's not as mature as you would say the steam reforming reaction, is that existing plants can be used. That if you just have an existing steam reforming reactor, we can actually just, instead of steam, have CO2 going along with it, or you can have a mixture of CO2 and water which goes along with it. And the second advantage of using something like the dry reforming is the fact that there are two greenhouse gases which are actually being removed in this particular case. CO2, yes, definitely. In fact, the greenhouse potential for methane is comparable or more than CO2, and that can also be removed. And if you're just looking in terms of the syngas, there are several different applications of syngas which can then be used. So you can use it in terms of producing methanol. You can use it in terms of methane synthesis, ammonia synthesis, or in terms of making Fischer-Tropsch chemicals, larger hydrocarbons, or in terms of other oxochemicals which are not methanol, like formic acid, etc. Okay, so now you have got the system, and we want to see what kind of catalysts which can be used, and the catalysts out here are usually supported. You have two components, essentially nickel and alumina, and then what we try to do is that we want to know the functionality, and we want to see that we can optimize this, and this is essentially what he showed, is that out here you can see on the left-hand side is methane conversion, and then you have got the other reactant, CO2 conversion. And out here on the x-axis are the different types of catalysts which have been used in terms of the metal. Out here is taking the amount of metal going from 10% all the way to 30%, 10% to 30%, same catalyst. So you're looking at the conversion of the two reactants. And you can see that as you're putting more and more nickel, you can see the conversion which is increasing. And this is seems like not a very difficult thing to understand, is that you're providing more metal, but then it goes on increasing, and then it decreases, and then you try to answer why did it decrease, and you say that, okay, the surface area which is exposed of this nickel actually falls, and actually that is what we have been able to characterize and show, that this one goes on increasing, and then there is an optimum after which this whole thing falls. So consequently, we know how to go about designing our catalyst and doing the reaction. Unfortunately, while we're doing this reaction, we can see that there's a lot of deactivation which happens. So a major concern in terms of running of any of this DRM reactions, or the dry reforming of methane, that is methane plus CO2 reaction, is that there's a large amount of carbon being formed, and because of this carbon formed, it looks like it cannot be used efficiently for the production of syngas or the production of hydrogen. So that is one design parameter in terms of the amount of nickel we can take in terms of the loading, and then we can add another component and say that that's another design parameter. And then we looked and searched around as to what are the other components one can take in terms of improving the activity. And yes, there are. You can take cobalt, or you can take iron, or you can take copper, and you can see that a few of them actually are behaving better than just the nickel alumina system, which is the traditional catalyst which can be used for most of these reforming reactions. And you can see that this nickel cobalt system is actually better than the nickel iron system compared to your nickel alumina system. And the worst is that if you're just careless and say that, okay, why not any metal, and say that why don't we use copper too, the answer is no. Okay, so there are some fundamental reasons as to why some things are more active than other, and that's where the next thing came in, is the answer is question, why did some metals improve and some metals did not improve. And that's where the handshake took over between one chemical engineering Jadavpur student working in my lab doing his PhD to another chemical engineering graduate student working in my lab doing his PhD, from Siddharth Sengupta to Kaustav. So that's where this teamwork actually helped very much in terms of understanding. First of all, both of them recognized that there is a strong correlation between the CH4 cracking and the turnover frequency in terms of the dry reforming. So in CH4 cracking, essentially what they're doing is taking a CH4 molecule and just without anything else and seeing that how does it form hydrogen, and there's the initial rate of formation of hydrogen, and then obviously it deactivates because there's a carbon being formed. And there is also, as I did mention before, there is the initial rate associated with the dry reforming reaction in which you are taking this methane, and then you see the concentration going down as a function of time. But if you're looking at both the initials, there is strong correlation between the two of these systems based on the catalyst. You have your nickel alumina, which is there. It's not a very good cracking catalyst, and it's not a very good catalyst for doing the dry reforming either. your nickel iron system, which is there, is slightly better in terms of the cracking catalyst. It is also slightly better in terms of reforming. Whereas you look at the system of nickel cobalt, that is actually much better than either of the two catalysts. Okay, so so what it seems that this rate determining step associated with both these two reactions are the same. And if you look in terms of the methane cracking reaction, it seems evident that the rate determining step would be the CH4 breaking up into a CH3 star on the surface species and a hydrogen. So that's basically what came out up to then. And then the challenge came up in terms of Costa, because he seems to be the more energetic. He seemed to have a longer time. He had the training, good training out here, the bachelor's at Jadavpur University Chemical Engineering Department. I gave him the challenge that if you want to do something really good, why don't you try to understand and get the science into this, and he did it. He did it. He took this electronic structures in terms of these particular catalysts and say that what is then the correlation between the electronic structures? What are those electrons doing in terms of these metal surfaces which are there for these alloy systems? You have got the three alloys. You have got a nickel cobalt alloy, you've got a nickel iron alloy, and then you have got a nickel copper alloy and the pure nickel system. And is there something which is different in terms of the electronic structures of these particular metals, or metal combinations or alloys? And so he did it on his own. He said that, okay, now the chemical engineering was chemical engineering. He took up this challenge of seeing the chemistry about it. They took up the challenge of looking at the DFT of it. And looking at the DFT, actually, he did find out that a very strong correlation in terms of the D-band center associated with these alloys. You're looking at the D-band center for a pure nickel metal, and this is the initial turnover frequency associated with it. And you can see that the nickel iron, as I said, is slightly better. Your D-band center is shifted. And when you took about the nickel D-band center and the nickel cobalt system, it even gives rise to a even better turnover frequency. And the nickel copper system is a bad system. Okay, so he could understand that the electronic structure associated with these alloys was the primary cause, the scientific reason as to why one alloy system was better than the other alloy system. And that actually gave rise to not only his understanding of why things were more active, but also why there was the difference in terms of deactivation which is happening, the difference in terms of the carbon which is being deposited, the difference in terms of that the nickel cobalt system, it was active, but also had carbon. Your nickel was active, not as active, but had lot more carbon. A nickel iron system was slightly more active than the nickel, but had less carbon. So the reason why was this carbon variation there in terms of this different catalysts, he also did in terms of the DFT calculations here along with another colleague of ours at IIT Jammu. He looked in terms of the absorption energy of carbon on these different surfaces, and he again found its correlation associated with these two. So, So that was not the end of the story. I mean, still, there was this deactivation which is there, and we needed to address it. And then, of course, that was the time period in which both the PhDs got over, and you start seeing who else is interested. And there was this other student who came in. I will not say that he's from Jadavpur University, but he said that he can still improve it. And he said that let's do some process engineering associated, not catalyst design anymore. So instead of having just CO2 and methane, which is going in, let's put a bit of oxygen. Okay, you would think that, okay, oxygen would be there, so is it possible that it can directly attack the carbon being deposited and burn that up? And he did that, and he found out that actually the conversions actually increased also. So it is not only that he find out that the reaction or the kinetics was more stable, but the fact that the conversion also increased. The downside of adding oxygen is that the CO2 conversion, which we are seeing also being improved, out here, the CO2 conversion actually decreased because now you're forming CO2 because of the presence of oxygen, which, quote unquote, was oxidizing your carbon. Okay, so he actually saw this and said that that you can improve, and I'll show you in the next overhead, that improve the conversion for this dry reforming just by adding a bit of oxygen. Obviously, you don't want to flood it with oxygen, because if you flood it with oxygen, you just have a combustion reaction, right? You will not have the formation of hydrogen out there. So just a small amount of oxygen, if you add, you are able to actually improve the conversion associated with this. And that was shown by Puneet in our group. And you can also see other kind of enhancements in terms of adding oxygen. As I did mention in the previous overhead, is that adding the promoters also helped. Cobalt was one kind of promoter which forms an alloy with nickel, and that improved their catalytic activity. And the same actually is sustained in terms of adding oxygen, where you can see an improvement in terms of the conversions under two particular conditions. One, where we're looking at 1023, which is the higher one, and one at 873, which is 600 degrees centigrade, as shown before. Okay, so, but both again, the same drawback is there, I must warn you, is that we're set out by saying that can we use and convert CO2? You'll have to be very careful with that, because the amount of conversion of CO2 actually decreases when we're starting introducing a bit of oxygen with it. Okay, and the carbon formation, that was the biggest thing. If you remember, the numbers out there was that the order of 45%, 35% carbon deactivation was there. But as soon as we started adding oxygen, as you can see out here, it goes from 30.5 to 0.3. 2.4 at higher temperatures. Temperature also has an effect. It goes down to 0.3. So there are two engineering parts we said that can be done, is that we want to remove or decrease the amount of carbon being formed. We use higher temperatures. Obviously, we have to make sure that the catalyst withstands those higher temperatures. And the second thing which we would like to do is that if you want to actually decrease the amount of carbon, we put small amounts of oxygen. So those are the two things which help us in terms of decreasing the carbon formation using either high temperature reaction or using small amounts of O2. And this actually has got a thermodynamic basis of it. We can look at the thermodynamic diagrams and see the carbon formation according to temperature and pressure, and we can say that actually high temperature does help in terms of decreasing the amount of carbon. Okay, then we can extend it even further. We can say that why do we stop in terms of just looking at methane, oxygen, CO2. We can then say that H2O can also be added. We can have tri-reforming. We can have not only tri-reforming, as we can look in terms of the power plant gases which are coming out. And if you look in terms of the power plant gases, this is the mixture. You have got CO2 coming in, you've got H2O coming in, you've got O2 coming in, and you've got nitrogen. Of course, you've got a lot of nitrogen coming in. But taking this particular composition, can we get something out of it? And then the answer is yes. And if you look in terms of what we can get out of it, Satyam showed that using his particular catalyst, where he has changed the amount of loading of nickel on top of this catalyst, he can actually go on increasing the amount of CH4 conversion, increasing the amount of CO2 conversion. The only thing, if you're looking at value addition, which is essentially your syngas, which is your H2 and CO, that ratio starts decreasing, even though all of them, we have a syngas ratio greater than 2, which is the recommended syngas H2 by CO ratio. Okay, so we have the conversion increase and the H2O by CO ratio decrease, which is not really troublesome for me, because we're still above the level of 2. The only bad part which I can see in this is the fact that we still have a lot of nitrogen out there. And the separation of nitrogen from this value-added product in terms of syngas is something which we have to be concerned about. Then, of course, it comes to the next thing, is that can we then do an engineering analysis? And that's where we are at, is that alongside this work of trying to define the catalyst in terms of the reactor size, the post-processing in terms of what are the products being separated, is something which we now are trying to do in terms of the flow sheet analysis and in terms of trying to find out a system where actually we can then separate your nitrogen out from your value-added products which are formed. I have another student who is working on microkinetic modeling, and what he's doing is he said that, okay, this dry deforming reaction is there, this dry deforming oxygen is, and he said that if you look in terms of this black box, you have got n number of reactions which are occurring, and these reactions people have played around with over the ages, and you have got, based on this n number of reactions, you have got people doing the DFT, finding out your K values, your activation energy values for each of these steps, and based on that, there are in this particular reaction network, there are 52 reaction steps which are going on. His challenge was then now taking this 52 reaction steps and looking and seeing if he can reproduce whatever we were seeing experimentally in terms of our laboratory. Okay, and he's also looked in the case in which oxygen co-feed is being used, and this is what he saw. Okay, he put those 52 reaction steps into it. He did not change any parameter which is there in the literature. He got those bunch of 52 algebraic equations under steady state, and he solved it, and he found out that existing parameters are sufficient to tell his product distribution. His product distribution in terms of not only your hydrogen and CO being formed, but how much methane and CO2 actually is getting consumed. So using this particular microkinetic modeling, he was able to then show is that when you're using oxygen, I did say that the conversion was increasing and your hydrogen was consequently also increasing, but he also showed that this cannot go on increasing forever depending upon the amount of oxygen which you're adding. There is some optimum amount. And that optimum amount of oxygen he was able to then show, or he's been able to show, which we have just submitted, is the fact that this actual amount matches up very cleanly with what the experiment do show. So he has then got a very good handle. But imagine now what he has done in this particular system is that all of this bunch of reactions which are happening in terms of this dry deforming, he could have just changed the input conditions. Instead of having CH4, CO2, and oxygen, he could have just had CH4, H2O, and he would have got the products. Okay, so now in this black box, which has got 52 reactions, he has got the power now of actually defining what the product distribution would be, depending, and by changing just the inlet conditions of this particular system. Okay, as long as he is just dealing with the network which contains CH4, which is coming in. He didn't have to have that. He would have gone CO2 at the inlet. He would have got CO2 and hydrogen at the inlet, and you would have seen something else which is coming out. And can he then map exactly what is happening in terms of the experiments? Okay, so that was the story, ended out there. We have been doing quite some time trying to do the propane dehydrogenation, taking propane to propene, and this propane to propene, we had Tarak doing a lot of work in that. And if you're trying to look in terms of this propane to propene, I'm sorry, this is the CO2 methanation, my apologies, where we're taking the CO2 and we're forming methane. The unfortunate thing of taking CO2 and forming methane is that this side reaction which is there. Now, let me tell you the story as to why this side reaction can be harmful. Now, if you notice that this is a reaction where you're taking CO2 and hydrogen, where you're saying that the industry it is used. The industry it is used because now we don't want the CO and CO2 going to the methane synthesis reactor. So instead, we want to have the CO and CO2 converted to methane. Now, methane is not harmful to the ammonia synthesis catalyst. Now, in the other way, you look at it in another way, it does, suppose you have now this CO2 which is there, which is something which we breathe out, and you're saying now you are confined in this room, there is no exposure to the outside, you're going to have a CO2 buildup. And that is exactly what people in the space station feel. Okay? In the space station, they are exactly feeling or experiencing the same thing, is that they are breathing in oxygen, and they're breathing out CO2, and they're losing that oxygen. So the oxygen is going with CO2, which if they're going to trap and dispose of, that oxygen molecule is lost. Now, how does one then capture that oxygen molecule is the proposal which came up by ISRO or by NASA, which is saying that the CO2 which is created, just to trap or to get back that oxygen molecule, they go through this methanation step. They go through this step in terms of making methane from it. They get back the oxygen in terms of water. Now, water they're going to dissociate and form oxygen. Okay? Dissociating CO2 to form oxygen is a very bad, is very difficult thing to do. So what they're doing instead is taking CO2 and converting it to water, and then water they do the electrolysis, because in the space station that is not too much of a big deal in terms of having the power in terms of solar energy. Okay, so that is the motivation which was there, and these are the current applications of it. Apparently NASA is already doing it. Unfortunately, there was a project proposal from ISRO. I don't know at what stage they are at. But in any case, the metals, several metals have been known to do this methanation reaction. And it was found out that by our group is that the nickel metal, which is active, if you start adding small amounts of iron to it, your activity shoots up. You look in terms of a pure metal system, and you start adding 25% of the metal being iron, 75 being nickel. You can see that there is a big jump in terms of the conversion which has happened. And this is independent at loading, at 10% loading or at 30% loading. You can still see that jump which is happening. Or if you look in terms of using different types of supports, you can look at the alumina support, a zirconia support, titanium, silica support. You still see those jumps which are happening. So the biggest jump, of course, is the alumina support, and that's what we stuck with, and then that's what Kostov stuck with. And the answer was, why did that really happen? And again, using his DFT calibers, he was able to show that if you're looking in terms of these three alloys, you can find out another descriptor, what we call it in catalysis literature, in terms of the number of density of states of the d orbitals at the Fermi level, which actually follows the same trend, which for methanation now, you have the nickel iron being more active than the nickel cobalt being more active than nickel. Nickel copper being least active for both the cases. Okay, so if you remember in the dry reforming, these two got interchanged. So the descriptor based on this particular reaction was different from one from another, and that's what he was able to address, is in terms of the electronic structure of these metal alloys, he was able to identify that in one case, it is the number of density of states of the d orbital, whereas the other one was in terms of the d band center, which is actually playing a role in terms of giving the scientific reason why one catalyst was better than the other. Okay, then of course the next step for us is now to see is that can we take this catalyst and actually form a device, a small device, which perhaps can be used in a space station, because space station, the space is limited. The amount of area, the amount of volume which they can give you is very limited. So is there a device which we can create which actually will take up this hydrogen in-house and convert this, do the conversion, and then proceed? And right now that's what we're at a point of. We're trying to develop the rate laws, and based on the rate laws, we're then able to make our reactors, our channel reactors, which can then be used as a device in terms of the requirements on a space station, my virtual space station, or in, for example, a place where it is not very friendly in terms of the oxygen being present. the last thing I will talk about, how am I doing with time? My time is okay? Okay. I'll try to quickly go through the rest. The last thing I will talk about in terms of the CO2 conversion reaction is associated with propene production. There is propane being converted to propene, and the reason why one wants to go to propane conversion, the market for propene is tremendous in terms of making this polypropylene, and that's about 70% of what can be done. Currently, the amount of propene which is required is got from two major sources. One is the steam cracking, and the other is in terms of the FCC unit, where you get propene, which then can be used for this particular process. There are, however, a need for getting what are called on-purpose means, and one mean is do the direct dehydrogenation, in which about 48% is used. You take a propane, do a dehydrogenation, use a dehydrogenation catalyst, the chromium alumina catalyst, and you form propene. And now propene, which is there, which can be used for this on purpose. However, this propane direct dehydrogenation has a few drawbacks. Catalyst deactivation occurs because of the carbon deposits. And there was a thought a couple of decades ago is that can this be overcome by using oxygen? When you use oxygen, it does not get thermodynamic limited in terms of the propene formation. The downside is that it might form a lot of CO and CO2 because of the direct combustion reaction. So we said that, okay, let's, instead of using oxygen, which I will show next, there was a lot of effort in seeing from our side is that can we use CO2 as an oxidant? The oxygen atom and the CO2, we say that we can link that with the hydrogen which is going to come out to form water, and so we are going to form propene, the water along with CO. So those are going to be the products which are going to be formed. Okay, so this is where Devo did play a very important role back in the 2010s. He's since then in IIT Hyderabad. But he recognized that this reaction which is there is that you have a propane using oxygen, we can form propene. The hydrogen which is there is going to form water. And if you have lots of hydrogen still there, then you have got the formation of the COX. So like a good chemical engineer, you say that, okay, now this is a series reaction. And then we want to say series reaction, we want to design the catalyst and say that, okay, you have to look at these ratios of K1 by K2, provided, of course, the mechanisms in terms of the reaction rates are the same. Okay, and they turned out to be very similar. And he said that, okay, I'm having a current system in which I want to improve the selectivity. I want this. I want the intermediate product. This is bad. And so I want high, that this selectivity should be high and the conversion should be high. Okay? So we want to go from an existing system where your selectivity is high, but when you're going for higher conversion, your selectivity drops. So this being desirable, the only thing which is going to tell us in terms of desirability is to look at this K1 and K2, or more correctly in the terms of the K1 by K2 ratio. And if you're looking in terms of the K1, K2 ratio, this is essentially what Devo did, is that he looked at several catalysts which are existing already commonly used by us in this. And he found out that, yes, indeed he can. The fact that he can make a catalyst which actually can improve it is going up from out here, the K1 by K2 ratio, which is at the order of 0.06, and he's gone up to about 0.254. Okay, so this, of course, he did long back. But since then, we have not been able to go much forward in terms of the oxygen. Because now everything is limited in terms of the amount of oxygen which is there. We're going to put more oxygen. You're going to have a combustion reaction. So these ratios are not leading to any commercial. Scientifically, yes. But using his engineering and scientific skills, he was able to show that this is the limit in which we can reach. We can't go beyond that. So it is almost like, okay, so that was the end out there in terms of the story. So he did essentially said that the proper choice of catalysts required looking at the K1 by K2 ratio, because otherwise the literature at that point of time was filled in with the fact that the selective was this, conversion was this, and all over the map. However, a scientific acknowledgement as to why they were the way they were was missing. Okay, so recently what we're trying to do is that instead of taking oxygen, we're taking CO2 now. When we're taking CO2, we have stopped the last part. We are going from propane to propene, but propene, there's nothing to take it to the CO2, because CO2 is already there in terms of the reactant. And it is possible, unfortunately very endothermic, and consequently it can be considered as a combination of two types of reactions where you're taking the dehydrogenation and this hydrogen which we are there is going to combine to form a CO. And as you can see, it is endothermic, which is the downside, whereas the one which used oxygen was exothermic. So we're looking at the first thing which we're trying to look at is in terms of the commercial formulation of a catalyst, which is when you're looking at the dehydrogenation reaction of going from propane to propene, we are essentially looking at chromia alumina catalyst. That's the industry standard in terms of doing this dehydrogenation reaction of propane going to propene. And so he made, instead of using alumina, he said that, okay, he'll use a different support. And of course, with all due respect, these supports are not very, compared to alumina, they're not very cheap. Okay, so he looked in terms of putting different amounts of, again, loading is an effect. So he put different amounts of chromia, and when he puts different amounts of chromia, he could see what are called molecularly dispersed surface species. But after a particular loading, out here, when you go from 2 to 3%, you start seeing what are called crystalline bulk Cr2O3. Now the consequence of that is actually tremendous. The fact that when you're going from monolayer coverages, out here we also call it monolayer coverage, above a certain level we are starting to have exceeded the monolayer coverage in terms of the chromium. So we have got molecular dispersed species when we are below 2, and 2 and below, and when we're above 2, you start following what are called Cr2O3 crystals. The consequence of that I'll just show you in the next overhead. But if you look in terms of what are the catalysts he made, he also made a chromium alumina catalyst of the same loading so that he could compare it 1:1, and then he could see that his catalyst is much better than a 1%. I must tell you, of course, that the surface area of these two material were different, and they were different as a consequence in the next overhead, which I'm going to tell you. That this chromia zirconia was much more active. Not only active, it actually was much more stable compared to your chromium system, alumina system. So out here again, I'm showing you what happens when we're increasing the loading in terms of this reaction of the dehydrogenation. And as you can see, and as I expect, you put more, it increases. But then when you hit 3 and try to say that, okay, I'm being greedy, I want to have more conversions, you're bad luck. You fall. Okay, so the whole idea is that we have increased it and it dropped. Now we can say that why it dropped, because we are forming, instead of just molecular dispersed species, we have now crystalline Cr2O3 which is formed, which is not effective in terms, as effective in terms of the catalytic reaction of the dehydrogenation compared to your molecularly dispersed species. So your monolayer catalyst is most active. And if you have the presence of the crystals, you would form a less active catalyst. And that's the formation of the crystal actually is a surface area related function. So if you have, for example, a larger surface area, you will be able to make many more of these molecularly dispersed species, whereas if you have a smaller one, you don't have that much of leeway of actually forming molecularly dispersed species. And in this particular case, if I do remind you that the zirconia was much more active than the alumina, but if you're looking in terms of the surface area, in terms of alumina, surface areas of the order of 200 meters square per gram, whereas zirconia was of the order of 50 meters square per gram. So the leeway in terms of improving the loading in terms of chromia alumina system is much more than the chromia zirconia system. So that is currently where we are at. We are actually testing both the system, trying to maximize the chromia alumina compared to the chromia zirconia system to see actually if we have managed to make the chromia zirconia catalyst a much more effective catalyst than the chromia alumina catalyst. The downside of the current state is that chromia is bad in terms of CO2. If you remember, we wanted to start off by saying that we're going to use CO2 as a soft probe in terms of doing this particular reaction. However, when we take CO2, our catalyst becomes worse. This is the dehydrogenation reaction of doing this particular. However, when we start putting some amount of CO2 in the stream, you can see that the activity has fallen. And not only the activity has fallen in terms of the amount of propane we're forming, but it also starts deactivating, which is not a good thing for us. Okay, so this is essentially what I wanted to conclude, is there are several CO2 conversion reactions have been shown that are possible, and many more which people have been doing and continue to do. However, what I've showed you is the reaction. The economic viability I have not shown you. Is that doing any of these reactions, you need energy in terms of the temperatures in which you're doing these reactions. Now, if you're having a particular temperature, there is amount of heat associated, and amount of heat associated will be directly related again to the amount of CO2 which is being produced. So we then consequently have to look at in terms of the net CO2 being utilized, if at all. So the net CO2 is going to be associated with the CO2 which is being used in the conversion, but CO2 which is also being used in terms of performing that requirement of energy for doing this particular conversion. So unless there is a balance in terms of those two CO2, it will not be a very effective way. It will be perhaps more effective than the current procedure of doing it, but in terms of going to net zero, it might not be as effective. So that's one of the things in terms of looking at the economic viability. And I hope I will be able to convince you a lot more research is possible in terms of improving these processes and developing new and better catalysts. And finally, this is something which I kind of wrote up, and I thought that I would share with you, is the Chemical Engineering Department at Jadavpur University has been an instrument in providing directions to the Chemical Engineering Committee since a century, and manpower for becoming leaders of the future generations of chemical engineer. They have certainly assisted me in my journey in having fun in research over the last several years, and for this, I thank you all.
Thank you, sir. Your topic on the conversion of carbon dioxide to some value-added product was quite impressive. Request to the audience, as we are running a bit late, so the question session, you can discuss it with sir during the lunch session only. Okay, I will now ask Professor Rajat Chakraborty, Head of the Department Chemical Engineering, to kindly come and felicitate our sir.
So next, I would like to ask Professor Debanshu Bhattacharya to begin his discussion. Professor Devanshu Bhattacharya is the GE Plastics Material Engineering Professor in the Department of Chemical and Biomedical Engineering at West Virginia University. His research interests are in the area of advanced modeling and simulation of energy generating systems, condition monitoring, fault diagnosis, uncertainty quantification, sensor placement, scheduling, control, and advanced manufacturing. Professor Bhattacharya has authored and co-authored more than 125 papers in peer-reviewed journals, 5 book chapters, 350 oral presentations, and 65 poster presentations. He is a co-author of the popular chemical engineering design book, Analysis, Synthesis, and Design of Chemical Processes. He is a member of the prestigious R&D 100 winning teams in 2020, 2016, and 2015 under the software and services category. In 2020, his team won the iChemi Global Award for a transformative microwave-based ammonia synthesis process. So, sir, would you please come on the podium and start your presentation? Thank you, sir.
যাদবপুর টক বলে আছে দেখুন টক
in a folder. Hello. Okay. Ready? Okay. Thanks everybody. Sorry for this technical problems here. So I was actually very happy to see many of the students attending this talk, and hopefully I get some questions for you, okay? No pressure, but really looking forward to some interactions with the students as well. This work actually that I'm going to present here, we have been doing as part of some ongoing project with the US Department of Energy. So the motivations, I probably do not need to give you any motivations. This is with respect to the CO2 capture processes and why we really need to do that. We know that the CO2 concentrations is actually keep going up, so we really need to do something here. The question is that what should you do? So first question is that there are many options, and this is going to differ from country to country. So one of the options is to do the post-combustion CO2 capture, and but the problem is that if you come up with a technology in the lab scale, it's going to take you 20 to 30 years to commercialize it. Can you wait for that long? And the other thing is, which US Department of Energy very fondly calls it, is the valley of death. Like out of these, more than 90% of the technology actually die a graceful death on its journey to commercializations. So question is, how do you know early on that what's the uncertainty in a technology? So for doing this, what we are trying to do is that for improving the sustainability, we want to do the accelerated commercializations with these technologies. So one of the key issues is that when you do the test runs in the lab scale, we do not get any notion of the uncertainties. So what we are proposing as part of this work is to do the design of experiment that actually can help you to understand these uncertainties, and then use that to maximize the learning with a fixed set of resources. So quite often, you have been given some amount of dollar and have been asked to say, develop this technology. Or you have been asked, okay, you have just 1 year of the time. So how do you do that? How do you actually quantify those uncertainties and then you utilize your fixed set of resources? This work that I'm actually talking about was undertaken as a US Department of Energy's first as a carbon capture simulation initiative, and then now it is ongoing under something what we call the CCSI-2. And this is an ongoing work for less than 10 years that we are doing in the space of CO2 capture. First, about the CCSI-2, this is a consortium of national labs. So this is the federal labs of US Department of Energy. Practically all labs working in this area work with us. Academia, we are multiple universities are there. And then there are industry, there are multiple industry works with us. And then those are not listed. There are more than 200 CO2 capture technology developers right now in the United States that we are actually working with. So the question is that if you really think about the design of experiment, the fundamental questions come is, well, we do it in the lab scale. What's the problem? What do we miss? So most cases, the design of experiments are done mainly considering at the input space. So we say, okay, these are the temperature, flow, reactor pressure, and all of that, and I can change all of that. But what we miss there is that what is in the output space? So I'm interested about the conversion, I'm interested about the yield. Can I design the input space to get some notion about the output space that I'm really interested in? But this inverse questions is actually very difficult to answer theoretically. So this is what we really want to get that. And then another issue that what we get here is that even if I do some of these test runs, can I take that into considerations for designing my new design of experiments? So what we want to do is that took a potential approach to address these issues. So first we try to consider the output space by considering a preliminary process model. And then we keep hedging it. We keep improving the process model as we collect more data. So I'll probably run one test runs, see what did I learn from that test runs, and use it for designing my next test run. So this was the whole idea. However, there are issues in terms of the uncertainties. Here in Calcutta, I don't think I need to explain what is uncertainty is, right? So for example, from Jadavpur, you want to go to Park Street, theoretically it should take you only just half an hour. But practically, it can take 2 hours, 3 hours, 4 hours, so that is uncertain. So this time uncertainty we know, but we do not know the result of this uncertainty. For example, say you have a plan to go to Park Street and say, okay, I'll take my lunch at Park Street, nice restaurant, you decided 3 days before, but on the way, you got so much delayed that you went to a restaurant in Taliganj. And also you have got all the mental agony and frustration as a bonus, right? This is uncertain. The action you take is uncertain. So we might know the reason for the uncertainty, but its result is very much unknown. So this is the issue that we really need to take into considerations for all of these. The approach that which we are trying to do here is something called a Bayesian sequential design of experiments. So Bayesian way is one way of defining the uncertainty in a space where we do not know anything about it. As we get more data and collect the data, we can actually get more understanding about the uncertainty. So what you do here is that you can have a more informed initial design. You say that, yeah, I know something about my process. It's not that I came up with some new process, I have no clue about it, but you say, okay, I know something. So with that, you start your initial design, and then you sequentially update your thing there. And then what you do here is that you design this from some space called H, which in this case, we are considering a discrete space. Ideally, it should be a continuous space, but this is mathematically intractable as of today. The issue is this general utility function that where you are taking this integral, inside this integral, there are two probability functions. So this probability, this is the probability of the parameter theta. So this theta parameters is your model parameters. For example, you are considering CO2 capture process, and you have got many model parameters. Like for example, how do you know what is your activation or energy of a reaction? If I give you a fixed number, who knows if that is right? I give you p exponential factor in an Arrhenius type of rate equation. Who knows what is the true value? I just give you a number. Am I certain about that number, especially for the new processes? So only notion about the truth can only be cast in form of a probability density function. So if I do that, so probability of theta given y, which is the data, comma, the design, as well as probability of y, the outputs given the design. This probability integral, you cannot actually analytically take these probability density functions because there is no closed form expressions for these probability density functions. So for solving this problem here, so this is overall objective is to max this utility function here, you have to resort to some kind of an analytical method. And we use here something called a MCMC approach, which is a Monte Carlo type of an approach, and I'll talk about that a little bit later there. So before I go further, first question comes is, let's have a quick look into what are my uncertainties, what I do not know, okay? First is we develop the properties model. We have the chemistry, thermodynamic, and transport models. These goes into a process hub models, and many of you have developed simulations model in Aspen Plus or ChemCAD, and you know that, like these are the ways you build your model, right? And then process hub model, and then it goes to a overall process systems model, steady state or dynamic process model. But if you see about all these measurements that you come in the lab, has uncertainties around it. All thermodynamic parameters, all chemistry, transport, kinetic models. And then these uncertainties get propagated when you are considering the steady state and dynamic models. So the question is, only measurement if you have over here, how do you know what was the uncertainty at this level? Or how the uncertainty in the chemistry model affects this final uncertainty here? That's really the question we are asking. Then we have the other thing about the lab scale measurement. Then we have the weighted wall column, bench scale, and pilot scale data, and everywhere we have the measurement uncertainty, okay? So all of these measurement uncertainty and the model uncertainty. I have a model, and I say, okay, this follows an Arrhenius type of reaction kinetics, but how do you know that it follows an Arrhenius type reaction kinetics? We do not know. It's a propositions. I talk about a reaction pathway. Do I exactly know this is the reaction pathways? We do not know. we have an uncertainty in all the models that which we consider. So question is, we have uncertainty in the model, we have uncertainty in the data, so how do I proceed, okay? But before I proceed forward, let's look into how it happens. So this is a typical solvent-based capture process. So in general, I just provide a standard template. There are many variations to these ones. So here is the absorber, the solvent goes here, then it goes to the regenerator, and then it comes back. This is a simple scale, simple configurations. Here we consider the properties, process, and the kinetic models. They get propagated through the process simulations. This is the thing which I'm interested. So these uncertainties in these properties model, when they propagated through your Aspen model or a ChemCAD model, this gives you an uncertainty in the percentage CO2 capture. So you do not get a fixed value for CO2 capture. You do not get a fixed value for energy requirement, but you get a distribution, okay? And our problem is that we want to have a percentage capture. We ask ourselves the inverse question that how should I change my operating condition to get a more certainty about these numbers. So before I go forward, I'd like to give you a very quick idea about the models that we are considering. This is a tower model. This is a rigorous two-flame model. We have considered both Ficke and diffusion as well as Maxwell-Stefani equations. This is rigorous resolutions of both of the flames here. We consider an ENRTL model, which stands for electrolyte non-random two liquids models. And we have the rigorous thermal and the chemistry models. So these are the individual stage models. So basically, the idea here is that this is the interface. This is only where the vapor-liquid equilibrium holds. So this is systems where simultaneous physical and chemical equilibrium holds, but the physical equilibrium only holds here. This is the vapor-liquid equilibrium. And then this flame, in the liquid flame, this is kinetically limited. And then in the liquid bulk, it may actually achieve the reaction equilibrium. So all of these scales needs to be resolved here. The main issue is these are ionic reactions. So there is ion transports needs to be considered through this flame. So this molecular transport goes to this flame at the interface, it reacts, and these ions get transported back into the bulk. So those transportations has to be considered here. So without resorting to any of these, I would like to know that other than that, we also have to consider many other properties models. So thermodynamic, transport, hydrodynamic, reaction parameters, and many other properties models. And many of these models that which we developed also in our lab, like this Morgan et al., these ones, Chinan et al., these ones actually we developed also in our lab. Now, so this becomes actually huge, gigantic model. So overall, this has got more than 150,000 differential algebraic equations. So that's what we actually need to take into considerations. So first of all, for the vapor-liquid equilibrium, I would like to notice here that on this, we are considering some real equation of state for the vapor side. For the liquid side, we consider the ENRTL model. This considers simultaneous physical and chemical equilibrium. I'm just basically casting it in terms of the matrix notations because that is what we actually use it for inverting everything here. I do not want to go with this model, but this is a very complex model with many parameters. So ENRTL model has got all these interactions between cation, anion, 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 cation, cation, and the molecular species with the cation and anion. So charge with the molecular species and their interactions needs to be taken into consideration here, so which gives you the excess Gibbs free energy, activity coefficient, and the excess enthalpy. So this is the heat that is required. So now the point I want to make here is, remember I said that I'm interested in knowing more about the energy requirement. But this energy requirement is also, we have the ideal heat of reaction, and then we have got this excess enthalpy. Notice that this is dependent on the Gibbs free energy, and this Gibbs free energy depends on many other things, which is the short range and the long range interactions, as well as the Born interaction. So all of these things actually have all of these effects here. Now, if we look into this excess Gibbs free energy model, without going into details into here, this is a very complicated model with many parameters over here. This is the energy interactions parameters and the Boltzmann-Skynes parameters that which we take into considerations. Then this long range and the Born terms also includes many other parameters that we are uncertain. Then we consider the transportations of the ionic species through the flame. And there we consider that there are many, the diffusivity parameters that which we have there. So now for as an example, if I give you a number like this, and these diffusivity parameters, there are only probably 1 or 2 labs in the world that can actually have the capability to measure these ionic transports. So these are uncertain. Even though there is a number given from a book, you do not have to trust it. Question that. So who knows what is the true values? So question is, we have all these uncertain parameters that which we have, including counter ion and the like ion binary diffusivities. So this is a space of the uncertain parameters that which we want to consider there. Now, before going forward there, so I wanted to show that how is the results actually look like. If you consider, this is the prior distributions of 2 parameters. So these are the only 2 parameters marginal distributions I'm showing here. So this gives you the starting with a Gaussian distribution that we have considered for these 2 parameters. When you propagate it through the Bayesian uncertainty quantifications and ask yourself these inverse questions, this leads to this posterior distribution. So you initially said, this is what I think the result is. But Bayesian uncertainty quantification says, no, the distribution should be actually like that. So this is what it says. This shows you the hydraulic parameters. So remember, hydraulic parameters actually affects the pressure drop through a packing. It also affects the hold up in a packing. Hold up in a tray are very much well understood, but not in a packing. Lot needs to be understood about the hold up in the packing. How much liquid is held up in a packing is a very complicated thing there. So this is actually showing you the distributions in terms of the packing related parameters, how it affects the hold up. We did the test runs in the world's 2 key pilot plants. One is the National Carbon Capture Center. This is in Wilsonville, Alabama, about 30 miles out of Birmingham, Alabama. And this is the technology center, Mongstad, somewhere in the North Sea. It's actually world's largest CO2 capture pilot plant. So we did some test runs in these 2 pilot plants. And I'll explain that what we actually did in these test runs here. So this was the test runs and the National Carbon Capture Center in Wilsonville, Alabama, was to develop a predictive model. This is actually getting a flue gas from a power plant, and this is where we are doing all the capture. And basically, we wanted to say that we would like to do the test runs. So let me see how it goes. So what we wanted to develop a predictive model. So we wanted to minimize our maximum uncertainty in the model, because that is going to be considered in a cost model. So if I'm telling you that I will require you $100 million, I want to say, no, I might require 80 or I might require 150 US million dollars for building a plant. So we want to ultimately cast it in forms of a cost. So the way we did it is actually, without going into the details here, I would like to say that we use the Markov chain Monte Carlo. There are many other samples, because this is a probability distributions. The only way you can do it is by considering some sampling methods. So the sampling methods we considered is a Gibbs sampling. There are many other sampling methods, but the Gibbs sampling is one of the methods that actually consider the distribution to be non-stationary. So that's one thing we wanted to do that. Marco Polo Hastings sampling is also very commonly used, but that considered the distribution to be stationary. This is an extremely computationally expensive problem, so we actually ran it on Amazon EC2 cloud. So this was actually run on an expandable Lawrence Berkeley Lab Amazon cloud that actually gave us access to tens of thousands of processor real time that we could access to run all these numerical calculations that we wanted to inverse these ones. Now, first, before going into forward with this, so wanted to say that, let's say, for example, if I get some of the experimental data, and then this showing you the model versus the data, and this is from that NCCC pilot plant, what do we notice here? That there are places where the model did not do a good job. Here, we think, yeah, it was reasonably okay. And then many other cases, we say that without intercooling, it did reasonably good job. But we have got at the lower percentage captures, we have got a lot of uncertainty in our model, actually. So the question is it the data or is it our model? How do I know? So first iterations, what we did was that we have this width of the 95% confidence interval. This is the prior distributions. What you really notice here, this is my uncertainty. So I'm saying here, yeah, here I might have, it is into 5% range, but here these places we have got very high uncertain range. Now, what we did was that we came up only with 15 test runs, and that actually shrink the uncertainty. So the idea there is that, do I know more about the process? So first I come up with, say, yeah, I know something. And then the question is, do I know what I do not know? Or how do I know what I do not know? So this is the way of asking that questions, and what we find there is that, notice this, again, if you're sitting at the back, you will probably not see these numbers here, but let me read this for you. Just, these are same scale actually, 2 to 11, so you can see that this is actually sitting below this, so that means the uncertainty got shrank. Well, we have got now more understanding. However, these places we are still uncertain. Notice that it did not shrink at all. So there are those cases I still do not know much about that. So what I did was we did the second iterations. So in the second iterations, we did something called an exploration versus exploitation. So this is something what is done. Exploration is basically utilize what you know. Exploitation is utilization of what you know, and exploration is go and look into a place where you do not know. So you need to balance both the things. Utilize what you know and try to find out what you do not know. So both of them. So we consider that one, and now we see that it actually improved us. So you see that all these places now got shrank here. So this is the advantage here. So only with these test runs, the uncertainty got reduced. But I like to note to you that there is a diminishing return. Even if I keep doing a test runs, it may not reduce your uncertainty after beyond certain level. That tells you you do not know something about it. That might require you to consider a different mechanism, different model. Maybe your model is not sufficient enough. Maybe your experimental runs are not sufficient enough. But it will tell you that I'm not learning anything more. So do not spend your resources on collecting data. You will not learn anything more. So this will mathematically tell you that. This is actually, we did also test runs at Technology Center Monster, Norway. So this was with some European CO2 capture technology developers. They gave us a challenging problem. They basically said, you know, many technology developers come to our pilot plant, and only question that they ask us, how do I know what is the optimal operating condition? What will give me the minimum energy? So can you tell me in 2 to 3 test runs, what is this minimum energy requirement? So this was challenging for us because we are not thinking that way. So we developed a test method to go and do that actually. So first thing to notice here is that there are cases, you notice that the model actually fails, many cases very miserably. So these are the places where there are operational issues at the low solvent flow rate in the stripper. It is basically showing you, so later on we realized that actually the solvent channeling through a part of the tower, and the model actually assumes an uniform distribution. Remember from in your transport class, we always consider there is a uniformity in the theta direction. It's not necessary. And this is what actually this pilot plant showed us, that there is variability both in theta, r, and z, in the radial direction, in the theta, peripheral directions, in the circumferential direction, as well as an axial direction. It's not uniform, that's an assumption. And this actually was very much clear through the test runs over here. So, however, without going into more there, I would like to say that for this case, we did prior and posterior 1 and 2. This is essentially telling you that this is initially what we started with, and then posterior, you saw that our uncertainty got shrank. Yeah, so we probably needed more, understood more, and this is that optimization runs. So initially, when we had the original model, we are predicting that our required energy is, the minimum energy requirement is here. But then as we collected the data and kept updating the model, this is what the model actually predicted, and now it is getting much closer to what the data says. Out of all these data, we only utilized about 5 or 6 data points, and rest of these I'm actually showing here just for the purpose of comparison, that the model actually got closer and closer to what the truth is, but we'll never know the truth. That once again, I wanted to tell you that here, in the pilot's gland measurement, nobody knows exactly how much energy is being required for you to actually, for the regeneration energy is very uncertain. So given with the uncertainty bound of these measurements, we are actually reasonably happy that it actually improved there. So I would like to say at the conclusions that we developed a methodology for accelerated learning for the CO2 capture processes. This is a very generic method. You can apply it for CO2 utilizations, especially for when you do it in the lab scales, pilot plant scales, any other bench scales processes. There, the question is that if I am not sure about something, can I actually come up with an approach to quantify those uncertainties? we evaluated this methodology by test runs at 2 pilot plants, which are largest pilot plants in the world there. This methodology is generic. You can apply it to anything, actually. If you come up with a reaction kinetics for a CO2 utilization process, and you say, I'm not sure about the reaction pathways, I really do not know about the mass transfer and the kinetic resistances, you can actually utilize this approach here. Interestingly, US Department of Energy, after seeing this success, they have mandated. Hello? Okay. Once again, you see, this was uncertain as well. I did not know this is going to fall off, right? So life is uncertain. This methodology is flexible, and we basically, what we saw that you can actually utilize this to understand when you are going to scale it up, what is going to happen. So these are 1 MT per day and 10 MT per day capture pilot plants. But when you want to do for millions of metric tons, what will be this uncertainty? So that was the whole idea. What we found here, and again, Dr. Rao and Day both actually highlighted this, that we found that we need a collaborations among all stakeholders. It's not only academic institute, we need industry, academic institute, government lab, pilot plant operators, technology developers. We all work together, actually. Because academically, there are a lot of things we did not know, actually. So as we kept talking to the industry more and more I know, and at the end of the day, we still know very little. But we are trying to understand, and we are trying to improve our understanding more, because we really need to accelerate the development of new technology. There is probably not going to be a single technology winner. As I said, right now there are 200 different technologies in the United States alone being developed. Who knows what's going to be the winner, actually? So, however, we need to accelerate the commercial technologies. Whichever has the potential, we need to improve that. So the work was mainly done by my student, Josh Morgan, with a lot of help from others. These are actually US Department of Energy folks, Lawrence Livermore National Lab. These are statisticians, Los Alamos National Lab, Dr. Christine Anderson Cook, she was one of the key statisticians we worked with. National Carbon Capture Center and Technology Center Mongstad, Norway, has got all our collaborators here. And this actually has got a lot of, the theory has been laid out through many of our papers. So sorry for rushing you through those, all of these ones. These are actually a lot of these papers that actually over the years we have published in this area that talks about the theory portion here. Finally, I would say that this is my group at that time, and this is actually Josh Morgan, who did all the work and spent sleepless nights in the lab. Like for months, he did not leave the lab and kept sleeping on the floor, because this was actually a lot of hard work, because this was a pilot plant operators. They say, tomorrow morning, I want to know what test runs I will run. So people sitting there in Norway with our time gap between United States and Norway, they say, tell me tomorrow what test run I'll do. And these simulations with the thousands of Amazon clouds, it still has got difficulty in converging. So he spent actually sleepless nights in the lab and work on this. So main work is by Josh Morgan here. And with that, I would like to end my talk, and I look forward to any questions. Please.
Thank you, sir. It was a wonderful topic. Your talk on improving sustainability through accelerated learning of carbon capture is worth knowing. Sir, now our Professor Ranjana Chaudhary ma'am from Department of Chemical Engineering will come on the stage and felicitate you.
All right, okay. Thank you. If anybody has any questions, please feel free to ask. How are you, Dr. Chaudhary? Nice.
How are you?
Good, good.
Hi, Zangan.
Our next speaker is the keynote. We will begin our keynote session now. Our next speaker sorry, there is a slight change in the arrangement. We will go for lunch now since it's already been 1:25. Sir, and whoever are there in the audience, you can go for lunch now and we will come back at 2:15 p.m. and resume the session. Thank you.
welcome you all after the lunch break. So without any delay, I would directly move on to our next session by keynote speakers. Firstly, I would like to call upon Professor Animanshu Ghotok to start his session. Currently, he is the professor at the Department of Chemical Engineering, IIT Kanpur. He did his BTech from IIT Kharagpur, MTech from IIT Kanpur, and PhD from Lehigh University. He did postdoctoral research at Cambridge University, UK, and Harvard University, USA. He was a visiting scientist at Leibniz Institute for New Materials, Max Planck Institute for Polymer Chemistry, Mainz, Germany, and Constance University. His research mainly focuses on bio-inspired design and engineering of materials, adhesion, weighting, friction, and fracture at soft interfaces, generation and application of hierarchically patterned surfaces, and flow through three-dimensionally oriented microchannels. He had published papers in various top international journals and several national and international newspapers. He has received Science and Technology Award for Research, ACRB Star 2020, CNR Rao Faculty Award, IIT Kanpur 2016, DOST Professor S.K. Sharma Medal, and ChemCon Distinguished Speaker Award, IICH in 2015. He is recognized as C.V. Sheshadri Chair Professor, IIT Kanpur 2019, and still continuing. He is an Fellow of India National Academy of Engineering 2018. He was also invited to speak at the Jordan Research Conference on adhesion science. Sir, could you please come on the dais and start your presentation?
Okay, so I thank organizers for giving me an opportunity to be part of this historic event that is going on over here. And I will not take much time, so I will like to start right away. So you can mic? Oh, collar mic. Yeah, please collar mic. Yes, I don't like this. Okay, so thank you so much. So I'm going to talk about elastocapillary effect and its applications. And yeah. So this is the outline of the talk. So I would like to introduce what is surface tension of liquid that most of you will know, Young-Laplace equation. Then I would like to talk about surface tension of solid. Then manifestation of surface tension of solid, elastocapillary effect. I will briefly mention about this particular Foppel-von Karman equation. And then I will show that this elastocapillary effect can be used for measuring measure the surface tension of a solid, estimate the concentration of a solute in a liquid, and one can also study kinetics of a surface reaction using elastocapillary effect. And then I will like to show you also that elastocapillary effect can enhance the surface reaction rate. So surface tension of liquid we have come across. Most of us know about this manifestation of surface tension of liquid in nature. Now, the way that we study surface tension of liquid is by putting dispensing a liquid drop on a solid, and then it has got these surface energies, gamma S, gamma L, and gamma SL, and we try to find out the minimum energy state. And after doing this, finding out the total energy and then minimizing with respect to the surface area through which liquid and solid remains in contact, one finds out this equation. This is called the Young's equation. So Young's equation, in a way, defines, now Young's equation, one can actually do many interesting things. Of course, estimate the solid-liquid interfacial energy. So, for example, if one knows what is gamma L and gamma S,
and the contact angle of, let's say, this particular liquid on the surface, one can find out what is gamma SL, like that. And once one knows gamma SL, then one can find out what is known as this work of adhesion. That means the gamma S plus gamma L, so these are the surface energy of the solid and liquid, and once they come in contact, so this is gamma SL, that is the interfacial energy. So this gamma S plus gamma L minus gamma SL, that defines the work of adhesion. And one can estimate solid surface energy also by this using the Young's equation, and then using what is known as this Good-Griffalk equation, that's the model equation. And so these are all very textbook material kind of in surface science. And then find out that how one can find out, so by using this equation one can find out the surface energy of a solid as well. Now the Young's equation as it stands kind of shows also a kind of force balance, in the sense that this gamma L cos theta plus gamma SL, okay, that is equated to the gamma S. So it is basically that. So this is the gamma L, so is the horizontal component of this is actually balanced. And so if gamma S increases, the liquid spreads, and if the gamma SL or gamma L increases, the drop retracts, like that. However, the normal component of tension, surface tension of liquid, that is normally ignored. So we normally do not worry about how this normal component of this gamma L sin theta, that affects this three-phase contact line, because most of the time we are dealing with a hard or rigid solid. The situation changes when this particular drop is dispensed on a soft surface. For example, over here, that when the liquid is placed on a soft surface, this vertical component of the surface tension, that pulls this liquid upward. Okay? As a result, there is a deformation that occurs at the three-phase contact line, and this particular deformation is called this, can be defined by what is known as this elastocapillary length. Okay? So here, so for example, like if E, the elastic modulus of this material is about, let's say, 100 megapascal to 10 megapascal, then this particular quantity is too small to measure. However, if let's say that this is water and silicon gel, for example, here E is 3 kilopascal, then this deformation is quite large, as you can see from the side view. So for these cases, this elastocapillary length can be 0.7 to 7 micron, which can be measured in microscopy, optical microscopy. And so one can actually write down that how the elasticity equation, okay, for this soft solid. And so this is the way that one has to write down this governing equation for displacement. So U is, let's say, the displacement over here. And this solution of this equation is known in contact mechanics. Okay? So this is known as the Buznik solution. And there it shows that what is the delta here. So the delta can be, delta is the distance, and what is the total deformation. So this is the strain there. So strain will be given by this. Gamma L sin theta is the vertical force, and then E is the elastic modulus, and delta is the distance at which you are looking at the strain. So this is the equation that comes out from this Buznik's solution for a point contact or point loading. Now here, there is something interesting here that's to be noticed. This is this epsilon zz, the strain that goes as 1 over lambda, 1 over delta. So what it means is that if the delta becomes smaller and smaller, then there is a stress or strain concentration that happens. So there is a kind of singularity that occurs, that if we let this delta close to 0, that means we come to the surface. So now there is a singularity here. The singularity cannot be there, that needs to be overcome, and in order to overcome that, what has to be there is surface tension of solid and its curvature. So surface tension of solid and curvature works in the opposite direction, so that way this singularity is taken care of. The manifestation of surface tension of solid we can see in many different applications. For example, like here is a mold, is a master mold against which we try to get, let's say, the pattern. We have to transfer the pattern, okay, using a soft jello like that. So here the PDMS film decorated with microscopic topographical patterns. So this is done by soft lithography. Okay, they do it all the time. And let's say gelatin gel of different modulus, that is used. So what can be seen here is that this is the pattern of the master replica of the PDMS, but once this gel is separated from this replica, the amplitude decreases drastically. So you will think that, okay, there is something has got dried and all that, but that is not correct. It is because of the surface tension of the solid that this, the amplitude of these patterns, okay, that decreases. So what it means is that surface tension, this shows that the surface tension is there and it actually affects. Then there are some another example, like this is very similar to the Rayleigh-Plateau instability in liquid. So liquid jet, that we know it breaks up into small droplets. So it so happens that this is a solid material. This is not a liquid, it's a solid. But this is agar gel and placed in different liquid or different, it is immersed in toluene, and it develops this kind of like Rayleigh-Plateau kind of instability. Okay? So surface energy of the toluene-air interface, okay, it is something like this, and that leads to this kind of instabilities. And it can be also seen some other experiments. And here, for example, like this is a contact experiment when a flexible plate is brought in contact with a confined elastic film, solid film. And here one sees this kind of fingering instabilities. And here, this fingering, the lambda wavelength of these instabilities tends to remain independent of the modulus or all other physical parameters, depends only on the thickness of the film. However, like if this particular film, this is of 2.22, let's say 2 megapascal, but is replaced by something that is very small, 0.24 kilopascal, okay, this wavelength of this instability that tends to change, okay, and that no longer follows this lambda is equal to 4h that you observe here, but it is like lambda is equal to 7h and something like that. And here also one can see this gamma surface tension divided by modulus, okay, this particular length scale that plays an important role. So what is surface tension and surface energy? So there is a relation between them. So for example, surface energy is the work necessary to form a unit area of surface by the process of division. So material is there, so you divide it, cut it, you create new surface area. So the energy associated with that new surface area, that is surface energy. And surface tension is the isotropic part of the surface stress. So what is meant by that is that this gamma SLE is the surface energy into area. Now if you change this energy, total energy, because of change in the area, so that will become this gamma SL, that is surface tension. So surface tension is related by this relation. So this is gamma SLE by dA, d gamma SL dA. So for liquid, changing in the area, okay, that doesn't change this gamma SLE because the liquid, the molecules are mobile. So as you increase the, let's say the area, surface area, the molecules come from the bulk of the liquid, bulk of the material to the surface, and therefore it can keep this particular gamma SLE constant. So therefore, for the liquid, we do not differentiate between surface tension and surface energy. However, for the solid, this quantity may not be same. For example, like if it is a crystalline solid, so there are molecules which are the atoms which are the lattices, and if you change the lattice length, then that energy will change. So as a result, for many solids, it is known that the surface energy and the surface tension, okay, that doesn't remain constant, that is varies, and it is known in the literature as the Shuttleworth effect. So what we have done is estimate the surface. So what I am going to present now is the work that we did, some work on this in this area, and we showed that we can measure surface tension of a soft solid by using curved surface of a microchannel. So here the microchannels are prepared by using a template. So template is a steel wire. So you just prepared a cross-linked material around this template, take out the templates and make this kind of channels, and it looks like something like this. So it is this is made on PDMS, polydimethyl siloxane, that many of you also work with, and then there is a fine channel there. The skin thickness of this particular film T0 can be varied, diameter can be varied, thickness can be varied, and when you put a liquid inside it, so as you can see here, that for let's say this liquid, say ethanol, okay, it bulges out. So that flat surface, it bulges out. And if it is air, then it slightly bulges in. So for air, it is actually slightly down. And for ethanol, it bulges out. DMSO, it again bulges out. Perfluorooctane, okay, that also bulges out. And there are like water, it will actually bulge, goes in, some things like that. So this effect happens not because of any swelling or like that. It happens because this particular liquid weights the surface of this channel, and reduces the interfacial tension or interfacial energy. So that energy or tension that leads to, that converts into elastic energy, and that shows up, that goes up like that. So one can see the circular the cross section of this particular channel. One will look that this yellow is the original this cross section, and that deforms into this kind of that deformation can be seen over here. And this is quite reversible in the sense that if you the same channel, you first put let's say it was initially air, so it was 6 over here, and then you put water, it goes to 7. You take out the water and put, let's say 3 here is DMSO, it will go over here. Take out the DMSO, put nitromethane, okay, it goes to 2, like that. So it is quite reversible, and here also one can see that if we, let's say, put ethanol over here and then it goes up, remove the ethanol, put water, or it goes down, then put ethanol once again goes up. So now the ethanol swells this particular material slightly, so they do not fall exactly on each other. But if it is nitromethane which does not swell it goes, it is completely reversible. And so this particular phenomena can be used for measuring this surface tension of this particular solid, and that is done by considering this solid air interface Laplace pressure and solid liquid interface Laplace pressure. So there are actually 2 Laplace pressure here. So the liquid is filled inside the channel, so there is a Laplace pressure across this interface, and that is like P atmosphere minus P liquid, like this. And then we have got another Laplace pressure over here, because this liquid over here and there is a solid over here. So this is PS2 minus P atmosphere is this upper side, and P liquid minus PS1 over here. So by combining all this, one can actually write this, what is known as the Foppel-von Karman equation. So this Foppel-von Karman equation is actually used in mechanics for describing the bending of a thin shell. And so here the right hand side is that delta P, the external force on the skin, and one can solve this equation, and I am not going to go into the solution of this equation, but one can do it by capturing the profile of this deformation, and one can get these interfacial energies and the stresses, interfacial tensions over here, like that. So for example, like if it is filled with air, then the interfacial energy is 22 millijoule per meter square, but the interfacial tension comes out to very close, 26. For example, like DMSO, it is 10.2, it is 8.5 over here, or like that. So what I mean to say is that this for this material, this PDMS, so this is a cross-linked material of chains, okay, for which, okay, this interfacial energy and the interfacial tension that matches with each other, that doesn't differentiate. So it is not like those crystalline solid. So this effect that we have used for looking at let's say the concentration of ethanol in water. So over here, let's say that this is the ethanol, ethanol in water in different concentrations. So like this is 100%. No, this is 0 here actually. So 0 is over here. That is actually air, water. At the water it is over here, and now as you increase the concentration of ethanol, the bulging deformation that goes on changing. So this is for, let's say, D is equal to 450 micron, and the skin thickness is 20 micron. And one can actually get this maximum bulging deformation, that is delta, and plot it with respect to these concentrations, and one will follow this kind of linear plot. So basically it gives a linear, almost linear relation, but doesn't necessarily it has to be linear, okay, relation between this delta and this concentration. And so now this kind of acts as a calibration curve. So if you have any other concentration of this ethanol in water, then you can actually find it out from this curve. And what happens is that if you change this skin thickness, okay, these lines will become parallel. So that's because of this, one can actually relate it by this von Karman equation, and one can find out that that can relate it. So that is possible, and one can also obtain this interfacial tension between this this aqueous ethanol solution and PDMS, and one can get these values for these different concentrations of this ethanol in water. And this is also true for DMSO and water mixture. So they are also, like, if you vary the concentration of DMSO in water, okay, you can get this kind of calibration plot, and here it is for 2 different thicknesses, so they remain almost parallel, as you can see. So one can actually find out the concentration of a solute in a solvent or liquid that is inserted into these channels, and one can see this bulging deformation by optical profilometry. And so we can actually looked at this particular phenomena. We used it for looking at this adsorption of a species into a surface, estimating intrinsic rate of a reaction and surface reaction like that. So I think because of time constraint, I will not go to this adsorption. I will skip it. I will just talk about, let's say, the surface reaction. So this PDMS has got what is known as the SiA, silicon hydride, and that participates in the curing process. And it so happens that this is also a good reducing agent. So when you insert into it an aqueous solution of gold, or let's say salt, gold salt, HuCl4, or let's say silver salt, okay, benzoate, silver benzoate, and then this salt gets reduced at this surface, and then it forms these nanoparticles. So these nanoparticles appear because of this kind of a reaction, which is known for some time now. Now, kinetics of this reaction can be examined by this elastomopapillary effect. Now, this is the proof that these nanoparticles are indeed forming. So, this is the TM or TM of this AgNPs and the AuNPs, and this shows that these are indeed gold nanoparticles, silver nanoparticles, okay, that form on this interface. And as this reaction proceeds, okay, the bulging deformation that actually goes on changing. So initially at t is equal to 0, this is almost like similar to that of water, and as the time progresses, this bulging deformation decreases. Okay, and that happens both for this AgB, that is the silver benzoate, and also for this HuCl4. This is 3 millimolar, is 10 millimolar, and it can be this concentrations can be changed. And one can actually relate this. One can think that this is an SiH is an excess. So what the reaction rate is a kind of first order. So if it is a first order, then one can write this kind of scaling the relation, and one can show that what is the reaction rate. So one can actually, without doing the actually measuring the concentrations, but just by measuring this delta, that is the bulging deformation or elastocapillary effect, one can find out this reaction kinetics. So this is the reaction rate one can find out, 0.23 here, 0.31 here. And one can do large number of experiments with different concentration, different diameter, and T0. So this is a collage of all this data, and you can see that the average comes out to be 0.38 per hour, like that. So they all almost like similar for all these cases. So one is to compare it with what is done conventionally by using this UV absorption, and here this absorption data, and this is with respect to time for these two different salts, and one can see that from this absorption data as well, that for this silver it comes out to be 0.23 and 0.37, so 0.37, 0.38, and so it is. So this whatever we get from this measurement of this elastocapillary effect delta, that almost matches with this UV absorption data as well. So why we want to emphasize that this this elastocapillary effect can be used for studying this kinetics of this particular surface reaction. So it is also examined also the adsorption of a species. So I didn't go through that, but yeah, so like that. Now I would like to talk to you about, take this particular discussion forward, and we like to see also that how elastocapillary effect can actually affect a surface reaction. So here what we use is called a partially cross-linked PDMS film. So we use 10% cross-linking agent, which has to be done to completely cross-link it. But it has been seen, or we have also seen, others have also seen that now, that if the PDMS film is very thin, 30 micron, because of this surface, it does not completely cross-link, or it cross-links at a very slower rate. So as a result, within 24 hours, it is only partially cross-linked. 48 hours, somewhat more cross-linked, like that. So, but then if it is less than 24 hours, it is almost liquid-like. So suppose it is a elastic film, PDMS film for 10 hours, and you put a liquid, let's say this water drop or this HuCl4 drop, and then you keep it. So immediately within few minutes, this particular liquid completely engulfs this particular this drop. So this piece of PDMS, okay, this is liquid-like, so that completely engulfs it, so which you can see from this sequence of images. So therefore, with this 10-hour cross-link, PDMS film is not good for us. Okay, those we do not work with that. So we work with this 24 to 72 hours, let's say PDMS film, which are of 25 micron thickness. And then you put this AU salt on the surface in two different modes. One is pool mode, another is drop mode. So these are hydrophobic surface, so therefore the drop, it forms a drop with 108, 110 degree contact angle for water at least. And for the AU, and we can also flood this surface with this particular liquid. So that is what we do over here. And now you can ask me that what is the modulus of this particular material, of this 24-hour material. So we do not have a direct way of measuring such a thin film and the modulus. So we again resort to my earlier, this instability work. And there I said that for a very soft film, this lambda that depends upon this surface tension of this material, and also the elastic modulus. And so therefore, from there we can calculate that Young's modulus comes out to be 1.62 to say about 17.5, that is 120 hours, and this is 7.5 kilopascal. Okay, by measuring the wavelength of this lambda and then relate it to the results which is there already published. And so these are the pictures. So these pictures actually show, if the light is not there, one can see that there is a gradation of gradual change in the color over here, and one can see also this particular surfaces can be subjected to UV absorbance, and one can see this kind of absorbance profiles. And from there, similarly for the AU salt also the same thing. Now for the drop surface also the same thing. So here it is the pull reaction, and here is the drop mode reaction. So in both the cases the reaction happens, and there is a circular, here it is circular of course, and one can get this absorbance spectra. And then once again we think that this is a first order reaction, and from that one can actually estimate this reaction kinetics. So the reaction kinetics, by considering this first order reaction, okay, for these different concentrations come out to be, let's say for 24 hours, yeah, so it is 0.7, 3.9, 3.4, this is for the pull, and for the drop case, it comes out to be 1.9, 3.2, 3.02, something like that. So the reaction was not exactly first order, but slightly larger than the above concentration, in the above concentration range, for example 1.33 or like 1.23 or like that, okay, but overall it is first order. And so if we consider that, then it so happens that for this pull reaction, the rate constant comes out to be 0.9 per hour, and for this drop reaction, it comes out to be 3.1 per hour. Everything else is constant. Okay, the concentration is constant, the same film. In one case, it is pull reaction, in another case, a drop reaction. And for this, this is for the AU salt, and this is also that. Yeah, so now here it is, let's say 100 hours. So that means the 100 hour, it is somewhat more cross-linked. So here this pull and drop, you can see the data, this absorbance data almost fall on each other. So there is no difference between this pull and the drop. And the reaction kind of rate, this rate constant comes out to be 0.48. So that is same for both the cases. And if you say, for example, silver benzoate, okay, then also you get this absorbance data for the pull and the drop case, and why you can see this, how it varies with respect to time, the maximum absorbance. And here again the same thing, 0.07 per hour, 0.24 per hour. So that means for the pull case, the drop case, the reaction rate is actually 3 times larger than the pull. And so, about 3.2. So what gives rise to this, this increase in reaction rate? So if we vary the quantity of the liquid, there is no difference. So it is almost same for drop case. Quantity of liquid does not actually vary. So is there any diffusion of any species from the substrate, or like is there any enhancement due to some contamination of the drop? So we check that. So actually, to summarize, there is no contamination, because if we put let's say water drop on this surface, the contact angle almost continues to remain same. If we put this HuCl4, okay, contact angle varies slightly, but that might be because of the reaction also. Contact angle becomes 101 to 105 degree. And if we take the drop liquid from the drop and then do this hanging drop experiment, then the surface tension remains almost same. So there is actually, and if you do the absorbance of these particular two different liquids, okay, there is no gold nanoparticles over here. So the gold nanoparticles that form, that is on the surface only, that is not at the bulk. So there is actually no contamination or that kind of effect. So what is the difference between these two cases is that for the case of this pull case, there is no 3-phase contact line. For the drop case, there is a 3-phase contact line. And that leads to this kind of effect. What is known as this elastocapillary effect that I started with, that let's say if it is water, then also it forms this kind of contact line. And if it is HuCl4 and it is kept for some time, I think it is for like 3 to 4 hours, then it spreads to some extent. But one, if it sees carefully, one will see that there is a lift of this particular substrate. And however, if this is with completely cross-linked film, and then there is no lift over here. So for a soft seal, there is a lift at the three-phase contact line, and that can be captured by various methods. So in one way is that you take out the liquid drop and cross-link it immediately. So and then you look at optical microscope, you will see something like this. Or one can see optical profilometry at the three-phase contact line. So if it is a complete 100-hour cross-linked, then there is a lift. Lift is this small. If it is 24-hour cross-linked, the lift is this much, about 25 microns. It's quite huge. And so what can do with this? So one can actually find out that what is this point of inflection? So the point of inflection is the point where this liquid comes in contact with the solid. And so that one can do by drawing these two circles, and this is a point of inflection. And then there one can do what is known as the Neumann's force balance. So that is the force, this is the gamma LV, that's the surface tension of the liquid, and gamma is the surface tension of the solid. And by considering, assuming, and it looks like that this particular meniscus or the solid meniscus that is symmetric about the two sides. So there is the gamma SL, okay, that's at the interface between the solid over and the liquid over here. So it looks like that. And then one can do this kind of balance, and one can get what is the surface tension of the solid over here and the surface tension of the liquid, okay? Surface tension of the solid liquid. So surface tension of solid and the surface tension of solid liquid, one can do by doing this force balance at this three-phase contact line. And one can actually go back to this particular definition of the surface energy. Now here, as I mentioned earlier, that for a amorphous solid, the surface energy and surface tension remains constant. That doesn't change. So one can say that the surface energy over here is actually equal to the surface tension. So just to clarify that this gamma S, gamma SL, these are surface tension. These are not surface energies. Okay? This Neumann's equation that we use, that's actually force balance. And so here, this surface energy, okay, is not different from surface tension. So gamma S surface energy is equal to surface tension here. So that is what it happens. So now one can actually find out what is this work of adhesion, okay, in the presence of this elastocapillary effect. So work of adhesion is surface energy. One has to calculate by subtracting from this equation. Here all the terms are actually surface energy. So gamma S plus gamma LV minus gamma SL, energies, and one can find out that it turns out to be W drop for the drop case 140 millijoule per meter square, and if one does the same thing for the pool case, then one has to write once again something like this. Now here, this surface energy between solid and liquid, that cannot change, that has to remain same. Okay, this gamma SL over here and then gamma SL over here for the drop and the pool case, that has to remain same because it's surface energy. Surface energy cannot change between these two different liquids, but the surface tension, okay, can change because it is with respect to air and it is in the vicinity, and so this term and this term are different. So here, this gamma S is 22 millijoule per meter square, and that is for the surface energy for PDMS. Over here, because of this elastocapillary effect, this gamma S turns out to be 71.6. So if you one calculate this, one gets this work of adhesion for the pool case to be 90.8 millijoule per meter square. So there is some difference. And one can write down this rate constant as this kind of expression, and from there one can actually get this expression over here by considering the W bar is the excess free energy per mole of this salt solution. So okay, one can actually estimate that by doing some little algebra over here, and then one can show that this ratios indeed goes as 3.2. So by this elastocapillary effect, one can actually explain this the increase in rate of reaction for the drop mode with respect to the pool mode. So I would like to summarize. So similar to liquid, solid too has surface tension. Intrinsic curvature of solid can be used to determine the surface tension of solid, and it is the solid surface tension into deformation is elastocapillary effect, and elastocapillary effect can be used for enhancing the surface reaction, and kinetics of a surface reaction can also be studied by using this effect. And these are students who did the work, Nitish, Subrato and Monmi Fukan, and financial assistance from DST ACRB, and thank you so much for your kind attention.
Thank you, sir. That was a great talk. So I would request the audience, if anyone wants to have any discussion with sir, kindly make it while having the tea outside. We are running out of time. Now I would like to invite Professor Abhijit Bawal, Sir of Chemical Engineering Department, to felicitate Professor Animangshu Ghatak, Sir. Abhijit Bawal, Sir. Professor, I would like to invite Professor Kajori Korgupto, Ma'am of our Chemical Engineering Department, to please felicitate Professor Animangshu Ghatak. Thank you, sir. Thank you, ma'am. So next, I would like to call upon Professor Dipankar Bandopadhyay. Professor Dipankar Bandopadhyay had obtained a BSc degree in chemistry and BTech in chemical engineering from Calcutta University. After completion of MTech from the Department of Chemical Engineering at IIT Kanpur, he served ANSYS Fluent India Private Limited for more than 3 years as a CFD engineer before completing PhD from IIT Kanpur. Presently, he is a professor in the Department of Chemical Engineering and Center for Nanotechnology, as well as the head of Jyoti and Bhupat Mehta School of Health Sciences and Technology at IIT Guwahati. He also has served as visiting faculty at Yunnan University at South Korea under the WCU program and KTH Sweden under the Erasmus Mundus program. His research areas encompasses thin film dynamics, soft matter physics, liquid crystals and theranostics, microrheology, clean energy, computational fluid dynamics, stability and instability of fluids, complex fluids, among others. He has authored 140 research publications in the international journals and has filed 21 Indian and 9 international patents so far. He is also one of the PIs of multiple Center for Excellences at IIT Guwahati. He is the recipient of NCL's Professor K. Venkatraman ChemCon Award in ChemCon 2016. He and his group at the Indian Institute of Technology Guwahati is the recipients of Gandhian Young Technology Award 2016 and 2019, BIRSC Srishti Appreciation Award 2017 and 2021. He is a nominated member of American Chemical Society, Royal Society of Chemistry and Indian Institute of Chemical Engineers. So I would like to request, sir, please come on the dais and start your session. Thank you, sir.
Thank you. Thank you so much for the kind introduction. First of all, thank you all for your invitation to this place. Jadavpur has always been, as a Bengali, this is one of those places, as a student, as a faculty, as in any form you like to come. And I was very humbled by the hospitality, especially the head, Kajori madam, and I can see a galaxy of other faculty members who were there who spoke before me. So thank you so much for the invitation. So today, I'm just standing between the valedictory, your tea, and this has been an extended session. So I will very quickly finish. I promise I'll very quickly finish after raising a few very important questions, right? And I hope all of you will be able to appreciate these questions, because whatever I am going to show today, these are all last 4 years, especially this activity that took off, during the pandemic. So I wish that, the young people, give me some attention to whatever I am speaking, and maybe I will be available to you as we discuss further. So you can see that, today I'm talking about something very modern, very recent, which is called the precision healthcare. And this particular topic is I think will be acceptable to the entire country post-pandemic, because pandemic, COVID pandemic was the first time when India as a whole country responded to this particular concept called precision healthcare. Before I start my topic, I like to tell that, whatever I'm going to present, these are all hard work of my students, right? And of course, we are all funded by very, very generously funded by the funding agencies. This is perhaps the best time to do research in India because the way it has been, these projects have been funded. If you have merit, if you have an idea, if you really pitch hard, you have the chance to really win a lot of funding opportunities, okay? So these are the people who have made this possible. So first I'd like to show you a video. This is the state of art of healthcare presently in the rural areas. This is one of those, one of those subsidiary health centers. Okay, this is one of them we have in Purulia, and the other we have in Bardhaman district. Okay, so these are all the situation of healthcare in the rural areas. This is the place where people go and people get their treatment. So those cycles you can see these through this, the workers, they go to the houses. Okay, this is the place how they climb up, and then they enter into this sort of centers where their fevers are treated, their malarias are treated. Many of the situations, what happens, like where even the delivery of pregnant women are done, right? This is the state of art. This is 2022 October. This picture has been taken, right? So overall, if I really talk about the healthcare ecosystem, it starts with, we are only getting the exposure of the tertiary healthcare center. But if you look at the overall infrastructure, these are all supplemented by the block level healthcare, then primary healthcare, health and wellness centers, supported by a few ASHA workers. This is the way the private and government healthcare infrastructure works in India. Okay? And this is where, as a young engineer of Jadavpur University, should see an opportunity. Why exactly, as an engineer, you should launch yourself, as a chemical engineer, you should launch yourself to work next 20 years, 30 years in the area of healthcare. This is where the opportunity lies, right? Next few slides, I'm going to explain you why this opportunity lies in front of you, right? So in a government structure, you have the district hospitals, community healthcare, primary healthcare center, sub-center, and these are, I will make these slides available with you so that you also have the numbers. So also the number pyramid, it percolates like this. Essentially what happens, since the facilities are not that good at the sub-center, what happens, the care goes to either the district hospital or to the tertiary care hospital. But believe me, 80% of the diseases, can be fixed at the level of, district hospitals or the subsidiary health centers or at the primary health centers, and tertiary health centers need not have a lot of population because, if you really get state-of-art infrastructure there. So we really need to work hard in terms of the technology, in terms of the development of different types of, ecosystems, so that, this healthcare can be provided, quality healthcare can be provided to the rural areas. And that's what we are calling as a precision healthcare, right? What is the emerging model? While looking at this, I was visiting last 2 years almost like all these places physically to see what's going on at these levels, at the level of tertiary. So suppose if you have the best hospital in India, okay, starting from that until which is the worst performing subsidiary health centers in the rural areas, right? So if you study that, if you study all the hospitals which are available across the globe, this is the model that is emerging over a period of time, that this is the era of data. This is the era of software platforms that is connecting people into different types of healthcare facilities. What is that? So suppose if you have a connected multi-specialty hospital, this is connected to the Global Center for Excellences so that it has knowledge coming into it. Okay, it is connected to the district hospitals, it is connected to the peripheral PHCs and SHCs, and then you have 24/7 online expert availability, collaboration with the Global Center for Excellences and district hospitals doing enforcing the best practices, right? If you can really come up with this sort of model, what happens? Like, you are able to really create digital platform for different levels, at this level, at this level, at this level, at this level. These are all digitally connected. So this is how we actually responded to pandemic. Most of us were not previously comfortable with the telemedicine platforms, but during the pandemic type, many of us, we took, not only we took advices, but at the end of the day, it has become a new normal to use the online platforms, right? Not only for healthcare, in different other aspects also. Today only we connected to NJIT and we did a lecture, right? So this has become a new normal over a period of time. And this is where the development needs to happen, where the young minds should emerge or immerse themselves into the activities, right? I'm going to show you some examples. If you surf Google for last year, what are the 10 top hospitals in the world, right? You will find 9 of them in US and only one in Europe. Actually, I was doing the study of this hospital only. Name is Karolinska. It's placed in Sweden, right? And Sweden is one country which was, if you look at the history, before Second World War, Sweden was a very similar country like India. Rather before First World War, right? It was a very similar country economy-wise, although very less populated, but economy-wise, it was, 2 countries you should study, Korea and Sweden. You will find, they were not very far away what we were, say 1950s, 1940s, 1930s, in those sort of situations. But today you see dramatically they have leapfrogged, way ahead of us. The only reason, the ecosystem that they have put forward. So similarly, Karolinska is the only European hospital among the top 10, right, which is in Europe. And, all these hospitals have one very common thing. These are all 500 to 1,000 bedded hospitals with all state-of-art research facilities, medical facilities, like starting from robotic surgery to transplantation, everything is there. But more importantly, the platform that is there is that these are all digitally connected hospitals, right? If you really want to book a bed from India, it will be very easily, pay-and-use model is already accessible. You can just, take a service, from a country like India, you go to Karolinska, right? All the departments are modular in nature. See, here you go to a cardiac department, nobody can change a cardiac department. If you go to renal urology, these are all standalone departments, right? But then in this particular hospital, first time in the history, people are using the concept of modular hospitals, right? Like, say, suppose if you have today more demand on cardiology will expand the base. Tomorrow, if it is urology will get the preference, right? So in that process, what has happened, they have created a very cost-effective model and a sustainable model to provide healthcare. Today, in this particular hospital in Europe, there is a footprint of about 1.5 lakh, per year population. They are getting treatment in a single hospital, which is one of the biggest role models in global perspective. And people are trying to see, actually this particular case came to me while I was studying. I'm going to show you as we progress. While I was studying about different types of hospitals, their infrastructure and all, how exactly they provide. So a few points coming in. You really need to get all the hospitals to provide create a kind of connected healthcare facility. The knowledge should flow very easily from one hospital to other hospital. You should have a central repository of data, and then you bring in the technology. So where are the opportunities? So for all of you, those who are still at about 3:30, today is the 3rd day of the international conference. Those students who are sitting, I have just created this particular slide for them. Okay? What is the opportunity? Opportunity is smart ICT platforms. This is where we are doing traditionally very, very well for last about 30 to 40 years, right? So we really need to focus now from traditional softwares, which was the banking softwares, which was the kind of other different types of softwares, to now the technological softwares. I'm going to show you one example. So data collection, storage, analysis, right? Connectivity, how do you put forward high bandwidth, delivery? And then what you need to do, provide to your population. When you really finish your career, is it possible if you're working in healthcare, and then what you are doing, you are providing evidence-based precision healthcare. I'm going to define precision healthcare in a few minutes, But then everything has to be evidence-based. If somebody has COVID, that needs to be proven with the help of a detection device. Otherwise, it cannot be a speculative case today, in 2023. Portable energy harvester, you can see those sort of subsidiary centers will be a completely different plane. If somebody has today morning only I was talking to some of the students, they are very excited that they are working on hydrogen and all. Question is that, can you use and make a kind of portable, hydrogen generator, which can replace these fossil fuel hydrogen generators, right? Low cost, sodium lithium battery photovoltaics. So this is going to solve the energy necessities related to some of the units, components of this, connected system. Highly skilled human resources are necessary. You need engineers, doctors, nurses, paramedics. Frugal portable diagnostics, I'm going to come to this. Therapeutics, precision medicine, administration, and waste disposal and management. This is very, very important in the sense of healthcare, right? Regulatory network compliances and the waste disposal. These are very, very important. So these are the overall areas which you can think about. Any one of them you choose and you put forward next 20 to 30 years of your life, I'm pretty much sure you are going to make it big. Right? So this is one thing what you can think about, but today's talk I have just focused on these three things. One is precision medicine, then frugal diagnostics, and then how exactly that is connected to the precision healthcare. Okay? What is precision medicine? Today you go to a medical shop or a kind of a doctor, that person gives you a paracetamol antibiotic of a known dosage. This is not going to work another 10 or 15 years. Right? So traditional medicine is, the radiation is high, the chemical loading is high, like surgery and all these things, these are happening in a more ad hoc manner. Most of the time, you don't need this sort of medicine. Whereas what is precision medicine? Precision medicine is really, really doing a kind of, your genetic sequencing, okay, and from there, it is really identifying the dosage, the drugs, and then from there, they are delivering the thing. What is the example? The example is this, that say suppose, this is the population of cancer patients, right? And then, you get the genomic data, you generate the clinical data. All these are sponsored by the health insurance, right? Then physician creates treatment plans. This is for an individual physician is very difficult to prepare. He or she may require a kind of software platform that this is the platform, I put the data into it, and from the data, the treatment plan comes out to be 1 for one patient, 2 for the second patient, 3 for the third patient. This is the way the medicine, see antibiotic dosages, that it varies with body weight and all, so they are not going to remain the same, right? And this is where, as a technology provider, as an engineer, right, you have a huge opportunity. Especially as a chemical engineer, you sit down with a very, very big opportunity. So first I show you a video where, I just, for the first cut of the video, the first part of the video, you may see what exactly is the diagnostics today. This is a semi-auto analyzer operated in one of the health centers nearby to IIT Guwahati. And then I'm going to take up from there what exactly we are doing at IIT Guwahati in order to replace this technology to provide precision healthcare. So you may just see this is a multi-step process. This is the step 1. This is a start with the daily maintenance. Then step 2, you are cleaning it. Okay, total 18 steps will be there. Step 3, you are checking the flow cell. Okay, step 4, you are checking the incubation, vacuum pressure, right? Step 5, you are labeling the test tubes in which you are putting the reagents. Okay, then you are putting the reagents for the sample test tube. Then you are putting the standard first in order to get the base reading. Then you are putting the serum into that, okay? Then you are putting this in the incubator so that some reaction, some require temperature, incubating. Okay, then you are doing the first one. For the base reading, around that, you are doing the standard calibration. And then, from there, you will be doing the sample. So this is how you are going to get, this is how the numbers are created. This is when you are giving a blood serum sample. This is how this is coming out to this. But what we have done, we have developed a device called MobiLab, which is this. So this is the cuvette in which you are putting the reagent. right? And in the reagent, you are mixing, first, you are getting the base calibration. This is a mobile-based device where the entire software is there, right? And then inside that, you are putting the serum, you are mixing it. After mixing, you are putting once again, and you are generating the data. So this particular device has been developed over last 5 years of innovation, which is also IoT enabled. So this actually does liver, kidney, different types of profile, which I am going to talk. So if a patient comes, you are going to use this software first with the date and all. Okay, you are going to collect the sample, and that sample you are going to put inside that device. Okay, and that device is going to give you the data. So what are we focusing right now upon? We are focusing on the non-communicable diseases, right? There are large varieties of diseases you can divide. One is called the communicable, one is the non-communicable. COVID was a communicable disease, but major killer in the world is non-communicable diseases. 750 million chronic kidney, 100 million pancreatic, 200 million chronic obstructive pulmonary disease, and 840 is chronic liver. So these are the diseases where things are detected, and you have to remember that there are in India perhaps 80% the disease are undetected until now, right? And there lies the opportunity for you young people, like get into, launch into, and then go for it. So this is the device which is IoT enabled, portable, with vernacular language. There is no such device today in India. Any auto analyzer, any semi-auto analyzer, they are not in any local language available. This is a big problem because the workforce which is working in the rural areas, most of them have issues with, most of the medical terminologies are very difficult even for us. It is very difficult for them, right? So this vernacular language is not there. Battery powered, I have already talked about, and then built-in incubation. Why? Because you are going for sensors, which can be normal sensors, which can be immunotherapeutic sensors, which can be enzymatic sensors. So for them, you need a little bit of light, little bit of temperature, all those things. So this is the typical landscape we are placing. So these are all heavy devices instead of this 200-gram device. The only disadvantage, it is sitting with what? It is not have, in an auto analyzer, you can do 1,000 samples in a single shot. Whereas in this one, you are going to do one at a time. That is the only difference, only limitation that you are sitting with. Otherwise, you may see cost-wise, every other aspects, you have advantage. So essentially, you may see these are the battery of 20 tests. Liver diseases, kidney diseases, we have started with 3, liver, kidney, pancreas, and then we are going to add, thyroid and cholesterol, right? So these are some of the field trial data we have. This particular device have been ISO certified right now. We have applied for CDSCO approval, and these are the data that has been submitted. These are all real data points in the subsidiary health centers. In total 5 hospitals, the device trials are going on for albumin, total protein, cholesterol, triglyceride, uric acid, glucose, okay. Then ALP, ALT, AST, bilirubin, hemoglobin. So total 20 markers. All those 20 markers are going to take care of the detection, the main day-to-day problems like thyroid, cholesterol, chronic kidney disease like albumin, total protein, urea, uric acid, creatinine. Okay, then liver, ALP, ALT, AST, and then albumin, and then total bilirubin, total and direct bilirubin, and then you have got the thyroid, liver, and then pancreas, which is amylase and lipase. So these are the battery of tests that is possible with this particular device. And this particular device is connected to what? This particular device is, how is it working? Schematically, you are putting 1 drop of blood serum, and then you are generating the data. This data is collected by a paramedical worker in the digital health center. Okay, this paramedical health worker is compiling the data, and that data is going to the doctor. Doctor is also having a teleconsultation platform with the patient, talking to the patient, and then the evidence is obtained, and from there doctor is able to give what? The delivery, the medicine, which is about to be the precision medicine. Based on the numbers only you can decide. Based on the level of infection only you can decide what should be the amount and dosage of the medicine. This is perhaps what is emerging over a period of time, another 10, 15 years, perhaps you may see this will be the status of healthcare. So I'm going to run another video, and this has been developed by a doctor. So in this particular platform is now integrated with our mobile app device. What it does, it actually will show you how a paramedic is doing these things. So paramedic, when somebody is coming to these subsidiary health centers or primary health centers, looking at a patient, the patient history is taken. Name, address, what are the symptoms, right? And from there, the paramedic is creating the history, and based on the different devices available, like say suppose simple pressure monitoring device, glucometer, like say suppose if mobile lab is available, all the data is integrated through this particular, the name of this software is called Uday. All the symptoms are first noted, and then all the parameters are noted through this software. And this software is going to generate a report which is going to go to the doctor who is sitting in the city, and they are looking at now the doctor is logging in, he's looking at the data. Okay, from there, it's not only like diagnosing the problem, but also giving the medicine, the amount, dosage, and then finally, the doctor has the license to give the prescription. So finally, after generating all this report, the doctor is creating the record, electronic health record, and then only the therapeutics are given, right? So right now we are working, this is a standalone device, for say suppose kidney unit 3, liver unit 3, pancreas unit 4, thyroid unit 3. So these are number of tests are required. So we are trying to make a bunch of devices, but then in future we are also using the advent of micro nanotechnologies in order to make a multiplex device. So in a single place, if you put a serum here, all these will say, suppose this is albumin, this is total protein, this is bilirubin, okay, this is T3, T4, TSH. So in a single bunch, initially we'll go for, say, suppose whether it's a kidney disease, or it's a liver disease, or it's a pancreas, or it's a thyroid, or it's a kind of heart disease. But then later on, the idea is that can you integrate in a single platform? With a few drops, you are able to give the entire data through the ICT platform that is there towards the doctor. I'm going to finish my lecture with 3 examples, how the newer technologies, how the novel technologies are going to change the picture even in that scenario. You know that cervical cancer is one of the 5 most cancers that are prevalent in the rural India, right? Breast, lung, prostate, okay, oral, and cervical. These are the 5 cancers which covers about 80 to 85% of the cancer patients in rural India, okay? And cervical cancer is detected with a very, very crude and very painful test called pap smear test. It's basically an insertion is given in the cervix, and then you scrape out the cervix, and from there you draw the sample, and from there you identify the infection associated with the human papilloma virus. But urinal proteins are very, very, it's a gold mine, because the same antigen that you look in that cervix matrix, okay, that is expressed in a very, very small amount in urine, okay, and that has been identified by a group of scientists in CDRI. She was actually working with this particular protein, and she suggested me, can we integrate this to this particular mobile app platform? Right? What is this mobile app platform? This is nothing but a UV visible spectrophotometer. Right? So what we did, we took a nanoparticle, we linked this with antibody, and then we thought that these are the linked particles, and then moment we put the antibody, what happened? We saw these particles, they got agglomerated together. And in the process, what we got a kind of shift in the UV visible peak, which was significant in nature. So we could convert, you can see there's a significant color change from wine red to violet, and that can be detected using this mobile app. So one platform related to the cervical cancer, which is one of the major problems, this can be a yes-no device at the rural areas. So you can really differentiate between the patients who are having cervical cancer or not. Second example, this is another very beautiful concept of nanotechnology we use. These are called nanoclusters. So you have a nanoparticle. If you it has a plasmonic response, right? It looks like, say, suppose sometimes it is red, sometimes it is yellow, based on its color, shape, and size, right? This you already know. But if you join them together, with an organic linker, this is nothing but an organic particle. This is CH2, 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 but having two thiol groups at both the ends. What happens? You can join the particles like a garland. Right. Now, when you do that, you can see that this is the Raman signal, which is of a single particle. But this is the Raman signal. This blue is the Raman signal for a linked. What is happening here? If you put two plasmonic particles just side by side, the interference of the surface plasmon resonance takes place. And that creates beautiful hotspots which you can really distinguish. So what we did, we took a PDMS surface. On top of that, we stabilized. So you see, this is a single particle. But here you may see that these are the nano twins. Okay? And these nano twins were integrated with a biopolymer called aptamer. This is nothing but DNAs. Right? And this aptamer was very specific to the E. coli bacteria. What are we attempting? In urine, we are trying to detect the E. coli bacteria, which is one of the major reasons of kidney-related problems in the rural area and the urinary tract infections, right? So what one can do, you have a PDMS surface, and on that you have an aptamer, right? And then this aptamer has very specific functional groups which attracts the E. coli into the base, right? So you can see that this particular device could detect the E. coli at a very, very low concentration. So the same sample can be utilized for the detection of E. coli in urine. So in urine, I am detecting two very important things with the same intervention. One is what? One is the cervical cancer antigen, and the second is the urinary tract infection. These are two nanobiosensors, okay? So I just finished that in IIT Guwahati, what we are planning that we have a school which I am heading right now, and then we are trying to integrate a kind of connected hospital, which is going to be, the structure is going to be like this, that this is an internationally connected multi-specialty hospital, which will have a PG medical program. Why? Because wherever you need doctor, if you put academic doctors, they are going to serve the business, right? Then you will have all the state colleges connected to this, health center, subsidiary health center, health and wellness center connected to this. And then you put AI data analytics facilities, and then diagnostics facilities, molecular therapeutics. You bring in all the regulatory bodies here, and then you bring in the entrepreneurs here. This is perhaps, the entire concept of the precision healthcare, where today I have touched upon very briefly on the precision medicine, then the diagnostics, and the data connectivity associated with that. Thank you so much for your attention. I'll be very happy to answer any questions.
Thank you so much, sir. Your discussions have truly inspired us. So I would like to invite Professor Kajori Kaur-Gupta, ma'am, to please felicitate sir. Ma'am, could you please come on the dais? Thank you, ma'am. Thank you, sir. So this brings us to the end of our plenary and oh, sir, you have one question.
I'm talking about precision healthcare. Medicine is one of the components of that.
The mobile lab application, simultaneously, a lot of samples can be checked.
Yes.
Because in NTPC, say urine or blood and everything, one person checks time by time. So can it be 100 samples can be checked at one time?
It can be, generally that is the way it is done. But say in auto analyzer, Say, what is the present mechanism of diagnostics? You give a sample. That sample is taken to a path lab. That path lab has autoanalyzer. But immediately as you give the sample, they don't start the autoanalyzer. They wait for 1,000 samples to come because that makes their break-even. Until 1,000 samples arrive, they cannot run the autoanalyzer because it will, until the plane is not filled, the plane will not fly because it will not lead to the cost effectiveness, right?
Yes.
So what happens, when you give a sample, you have to wait for, your sample waits for about a day and a half before the readings are taken. And this is where the most of the inaccurate detections. So suppose I have diabetes, my samples will not show glucose accurately if it is done tomorrow afternoon because serum is one particular material which denatures in 15 to 20 minutes. It's about 20 minutes. We have seen the readings. In 20 minutes, 30 minutes time, the properties of serum changes heavily. Right? So, there are two aspects of the question that you are asking. One is, how many I can do? This is a thermodynamic aspect. Second aspect is the kinetic aspect, how fast I can do. As soon as I can do after the removal of because after you remove the serum, you also have to remove the corpuscles. Before you put when you draw the blood, corpuscles has to be removed, then the serum has to be separated out and that serum has to be placed for the detection, right? In this sort of device, in the multiplex microfluidics platform, with a single drop, we can really distribute to n number of as many sensors as possible because these sensors are going to detect and that directly will go to the mobile phone. So you have to address two problems. One is multiple and then minimum possible time.
So in an NTPC pathology lab, this mobile app can be well used and I think multiple samples can be checked together.
That is already there in autoanalyzer. In autoanalyzer, you already have those things. If you look at an autoanalyzer, they are already doing that. But they are doing, first thing is that they are doing at a cost of 800 rupees, 500 rupees, 400 rupees for you per sample. Cost is very high. Second is they are doing at after long time. They are doing after 3 hours, 4 hours minimum. That is not
sir, sorry for the interruption,
okay.
sir. Actually, we are
so
running
cost
out
will
of
be
time.
less, much less.
Much less.
Okay, thank you.
So this brings us to the end of our plenary and keynote sessions. And it has been such an honor to be a part of this wonderful event. On behalf of the organization, I would like to extend my heartfelt gratitude to our esteemed guests for being here with us. We are really enlightened with their knowledge and presence. So now we are closing this session. Thank you once again. And here will be a valedictory session from 4 p.m. onwards. Thank you all.
Good afternoon, everyone. After 3 days of interaction, chemical engineering, the glorious centenary celebration program comes to an end. Though the 3 days passed in a flash, the rigorous preparation started 6 months back. As students, it was one of a kind of an opportunity to be a part of this journey through thick and thin, starting from designing mere brochures to bringing a grand program on stage. We are also extremely grateful to our noted faculties, our staff members, and our seniors for having faith in us and trusting us with responsibilities. A special mention to all our guests, dignitaries, and speakers for embracing this celebration and being a part of this program. It was a great learning experience for all of us, and we hope to be a part of such events in the future. Thank you.
We would like to conclude the conference session by the distribution of awards by the joint conveners ICIS for presentation in the technical session. Thus, I would like to call on stage Professor Ranjana Chaudhary ma'am and Professor Kajari Kaur Gupta ma'am. Best Oral Presentation Award, Rupayan Pal.
Transport process and process simulation and system engineering. Rupan Pal.
Best Oral Presentation Award for Process Intensification and Integration, Ritika Shamanto. Best Oral Presentation Award in the category of Biofuels and Bioprocess and Biorefinery and Sustainability to Shundipon Bhomik. Best Oral Presentation Award in the category of Waste Management and Pollution Control Type 1, Orko Prabho Roy. Best Oral Presentation Award in the category of Catalysis and Reaction Engineering to Smita Mondol. Best Oral Presentation Award in the category of Petroleum, Petrochemicals, Coal and Carbon Dioxide Capture, Storage and Utilization to Orindam Mondol. Best Oral Presentation Award in the category of Nanomaterials, Composite and Applications Type 1 to Preetha Ganguly, IIT Delhi. Best Oral Presentation Award in the category of Waste Management and Pollution Control Type 2 to Deepshikha Tamili. Best Poster Presentation Award to Rishita Modak. Best Oral Presentation Award in the category of Nanomaterials, Composite and Applications Type 2 and High Polymer Composite to Shampod Chorkar from Jadavpur University. Best Oral Presentation Award in the category of Energy Generation and Storage to Shantanu Mondol, Chemical Engineering Department, JU. Best Oral Presentation Award in the category of Waste Management and Pollution Control Type 1 to Orko Prabho Roy. All the certificates will be distributed from the counter. Kindly collect them. Thank you. Thank you, ma'am. Now I would request the Dean FET, Professor Bhaskar Gupta, to kindly come on stage. Okay. I would request our Finance Officer, Mr. Gaur Krishna Pattanayak, to come on stage. HOD, Professor Rajat Chakraborty, to kindly come on stage. I would also request Professor Siddhartha Dotto to kindly occupy his seat on stage. I would also like to request Dr. Shulolit Bandhopadhyay to kindly come on stage. And lastly, I would like to call Mr. Dipankar Das to come on stage. So we would like to start the occasion with the felicitation of the finance officer by our HOD.
So, Mr. Gaur Krishna Pattanayak, the finance officer of Jadavpur University, is with us throughout the journey of the organization of this particular centenary celebration program. He has been instrumental. He has supported throughout, and he has been inspiration also. And without his support, we couldn't make it possible, actually. So I would request our finance officer to say a few words.
Thank you so much for inviting me here and giving the opportunity to talk. Professor Siddhartha Dotto, our former Vice Chancellor and Professor of Chemical Engineering, and honored guests in the dais and guests of the dais, teachers, students, and non-teaching staff of the Chemical Engineering Department. The celebration program of the centenary of Chemical Engineering Department is planned 3 months back. Actually, we have started the process effectively in December. Prior to that, the movement was very slow. Since December, we have started our given a rigorous effort to complete the requirements as desired by the department. We have ensured that there is no problem in the process. From the administration, from the finance point of view, whatever support required, we have provided that. And the journey of 100 years, in the last 2-3 days, that may be discussed at every level in academic and other issues. What is the contribution of the department to not only to the university, but to the society, but to the country as a whole. Our former students are placed everywhere in the world, in the universe. They are serving many institutions, many institutes. They are heading many reputed organizations also. So it is a matter of pride for all of us that the department is completing 100 years and we are celebrating it now. For COVID, we are a little bit delayed. But finally, today is the concluding day. So I thank to Professor Rajat Chakraborty, being the present head of the department, to take the initiative and to lead the team. Under his leadership, the departmental staff, students and teachers all were united and given their effort to make the program a grand success. I hope we could reach the level of expectation to the alumni and to the outsiders, what we have planned and what we have finally implemented. I think we have satisfied all concerned. Thank you so much. Thanks for the audience for patience hearing. And this is my actually last year in the Jadavpur University. So I take privilege to be present in such a august gathering of a departmental centenary. It's a pride for me also. Thank you all.
Thank you very much, our finance officer. And now it's over to Megha.
As we are concluding our centenary celebration program, Chemovescence, I would like to call on stage our convener for summing up their experience.
Okay, so we are about to end this 3 days long centenary celebration program today. And everybody is to some extent tired, particularly the teachers, staffs, all the students, scholars, and all who are associated with this journey. First of all, I would like to thank everyone out here and not here present. A big thanks to all for supporting us throughout this journey and throughout this entire program. The delegates from the companies, the alumni association who are associated to some extent in the program for the purpose. But I would say that the university authority also helped us a lot, and overall there has been support from all sectors. And few alumni I should mention here that Mr. D.P. Mishra, he has helped a lot in getting the sponsorship. Dr. Ashit Das of Reliance Industries Limited, he has also helped in getting the principal sponsorship. So basically 2-3 alumni are actually throughout the process helping us in getting most of the sponsorship in particular. And few batches of this department, few batches means some of the alumni belonging to certain batches have helped a lot. I don't want to mention particular batch name, but in fact, some of the alumni contributed individually, as you know, that I don't want to reiterate here, but many of them personally donated a big amount to help us organizing this mega event. And I also would like to thank all our committee members. The committee members consist of all the teachers of our department, particularly the coordinators and the joint conveners of this program, the research scholars of this department, the students, UG students, PG students, and all who have helped us, particularly the students convener and our coordinators, 4 coordinators. As you all know the names of all the coordinators, but I would like to mention their name on stage. Dr. Shashwat Bose, Dr. Sudeshna Saha, Dr. Mehbub Rahman, and Dr. Radna Dotto. So, and joint conveners of the International Conference on Chemical Engineering, Innovation and Sustainability, led by 3 professors of our department. Professor Ranjana Chaudhuri, now the senior most professor of this department, has been very much instrumental not only in organizing this particular conference, but she has been actually very much supportive throughout the journey, and whenever I wanted to get any advice, she gave me without thinking a single second. And also I would like to mention Professor Kajuri Kaur-Gupta. They are all my teachers actually, and also they have been relentlessly supporting this event throughout the journey, and in the period of crisis, they helped us a lot. Professor Papita Das, the next head of the department, has been associated with us definitely throughout the long time. And so apart from that, our non-teaching staffs, Mr. Osim Bhattacharya, Mr. Sanjay Rai Chaudhuri is the librarian of our department. Suraj is there, and Noyon and Komul. Komul is not found here. But all these office staffs, without their relentless support, without their untiring support, untiring effort, we couldn't make it possible to organize this big event throughout these 3 days of journey. So the students, particularly the coordinator, I would like to mention, I do not want to mention particular names because there are so many students who have been associated with this program, and so it is difficult for me to mention specific names, but definitely they have been very much, particularly UG4 students, few of them, as you know, they have been very, very supportive throughout the journey, and some of the scholars, they have been also instrumental throughout the journey. The scholars, many of the scholars have given their best effort. And so UG4, UG3 students particularly, they have been very much cooperative, very much, So apart from that, we have got support from the alumni, and definitely the university administration, starting from our Pro-VCs, VC, and as I've already mentioned, the finance officer has been always supportive throughout the journey. And in fact, so this is a long journey. We have started our invitation process in the month of September. And as you know that we have been able to bring to our department also 2 of the most renowned chemical engineers of the country, Padma Vibhushan, Professor M.M. Sharma, Manmohan Sharma, and Professor R.A. Masalkar. So they have been there, and not only that, they went to our department to inaugurate the newly developed meeting room just beside the room of the head of the department, and we have been very fortunate for that. So it is difficult to conclude, and it is difficult to mention all the names. In fact, starting from 25th of February until 27th of February today, there have been many luminaries. They have come to our program, they have shared their views, and they have enriched us all through this program. And I think not only the students and scholars, but all of us will be definitely guided by their advice and their support throughout, not only for 3 days, for the coming days. We will be definitely getting their support, I think, and I have just come to know that some of the industry houses are showing their interest in some of the research areas, and they are trying to collaborate with the department in some specific research domain. So that would be definitely very much welcome from our end, and we would like to definitely request the industry houses to come forward to cooperate with us in specific areas where they have interest to collaborate. So definitely our former teachers of this department, like sitting with me, Professor Siddhartha Datta, everybody knows him, former Pro Vice Chancellor of this university, and others who have come, who have joined us during these days. There are so many former teachers, Professor A.K. Mitro, Professor Pinaki Bhattacharya, Professor Chandan Guho, Dr. Moran Chandra Saha, and others have joined us, and they have shared their views. So along with that, we have got the participation from the alumni. So I am thankful to everyone. I am thankful to everyone, and I think this will lead to more and more sustained development of the department and also university as a whole. We are actually looking forward for some collaborative efforts with some of the industries like Excel Industries. For example, the chairman of the Excel Industries came to our program, and he has expressed some desire for collaboration with our department, because earlier they have not recruited any student from our department. Excel Industries, if you just search on Google, you will find how big the company is. So it would be definitely a, opening of a new era for the department if we can collaborate with new industries which are trying to come forward to collaborate with us. So I think, and today, throughout these 2 days of journey of the international conference, here we have got the privilege to get the presence of renowned professors coming across the globe, from UK, USA, and also leading institutes of India like IIT Kharagpur, IIT Bombay, IIT Guwahati, IIT Kanpur. And so we are very much fortunate that we have got their support, and definitely that will lead to some more collaboration with our department, with the IITs and other leading institutes of the country, and also not only restricted to country, abroad as well, because sitting just beside me is my student also once upon a time, Shulolit. He is now in the Norwegian University, NTNU. So we have got a lot of international collaborations actually. So in fact, sometimes what happens, the collaborative efforts also require the approval of the university authority, because in some areas of collaboration, there require certain policy of the university as a whole. Means whether we would go for long-term internship or short-term internship, there are certain policy decisions and other associated factors for that. So accordingly, we need to decide upon a specific collaborative program. So in that sense, we are open to all the institutes, domestic or foreign, and we are looking forward to more and more collaborative research and development activities with different institutes and industry houses. So any proposal, any suggestion from institutes and industries are highly appreciated, and we would look forward to that. So I think I have tried to just summarize my experience, and I hope there will be a new beginning, and we'll look forward to more development for our department and university as a whole, in terms of research collaboration, in terms of placement, in terms of overall development of the department and university. So with these few words, I now just want to pass on to the next speaker. Thank you all once again.
I would request Mr. Alok Basu, Secretary of JCEAA, to come on stage. So, Mr. Basu will be felicitating our convener, Professor Rajat Chakraborty, Head Chemical Engineering Department, Jadavpur University. I would request Professor Roger Chakraborty sir to felicitate the coordinators, Dr. Sudeshna Shaha, Dr. Ratna Datto, Dr. Mehboob Rahman, and Dr. Shashwat Bose. I would like to call on stage Dr. Sudeshna Shaha, ma'am. Next, I would request Dr. Ratna Datto to come on stage. I would request Dr. Mehboob Rahman sir to please come on stage. And I would request Dr. Shashwat Bose sir to kindly come on stage. Thank you, sir. Next, I would like to call on stage Professor Ranjana Chaudhary, Joint Convener, ICIS, ma'am. Please. I would like to call Professor Avijit Bhaval, sir, Convener, Logistics and Hospitality. In the meantime, I would like to call on stage Dean FET, Bhaskar Gupta. I would like to call on stage Professor Kajori Gupta, ma'am, Joint Convener, ICIS. Kajori Kaur Gupta, ma'am, Joint Convener. I would like to call on stage Professor Debashish Roy, Internal Committee Member. Professor Ujjaini Shorkar, Internal Committee Member, is requested. Next, I would like to call on stage Professor Papita Dash, ma'am, Joint Convener, ICIS. Next, I would like to call on stage Dr. Chonchon Mondol, sir, Convener, Finance and Accounts. I would like to call on stage Dr. Ranjana Dash, ma'am, Convener, Registration, Website and Media. Next, I would like to call Dr. Shamol Roy, sir, internal committee member. Next, I would like to call on stage Ms. Sujata Sardar, ma'am, Joint Convener, Logistics and Cultural. I'd like to call on stage Dr. Rajkumar Das, sir, Joint Convener, Logistics and Cultural. I would like to call Mr. Taposhki Maiti, sir, internal committee member. Next, I would like to call Mr. Sanjay Roy Chaudhary, sir, internal committee member. I would also like to call on stage Mr. Oshim K. Bhattacharya, sir, internal committee member. Thank you, sir. Thank you, sir. I would request our HOD to felicitate our Dean FET. Now I would request Professor Siddhartha Dotto, sir, to kindly come up and share his takeaway from the program.
Professor Bhaskar Gupta, Dean, Faculty of Engineering and Technology of our university, Mr. Gaur Krishna Patnaik, Finance Officer of our university, Professor Rajat Chakraborty, our head of the department, Sulolit, Dipankar, our alumni, and serving the industry as well as the academic institution outside India also. We are proud of them. My dear students, faculty members, staff members of our department, it's a happy occasion. It's a long journey, 100 years of chemical engineering in India. Teaching, research, and practice. It's a glorious journey, I should say. And on behalf of the former faculty member as well as the alumni of the department, I congratulate the faculty members, the researchers, the postgraduate students, undergraduate students, our staff members for organizing this program in a befitting manner. So I congratulate all of you. During the last 2 days and today also, we have been listening to the conversation, presentation, advices, suggestions from experts who are in industries as well as in academic institutions. I know the department has weakness, strength, opportunity, and challenges, many challenges. Considering all these, I think you have already taken note of the suggestions, advices from experts. You should sit together and should come out of a solution and accept the challenges. Even I would request you to forward your suggestions, advices to AICTE, UGC for further strengthening not only the engineering discipline, but in particular the chemical engineering discipline in our country. From the national level, we have been hearing since the beginning of this century that we must go for engineering science. Not only engineering and technology, we will go for engineering science. We have more component, we should have more component of science in our syllabus, in our curriculum. In fact, many countries, particularly I will be talking about the chemical engineering. In chemical engineering field, what we have seen and still observing that there are a lot of changes. There are more and more science subjects in the syllabus, in the curriculum. Because the industries, they are saying that we need scientific solution of the engineering problem. So already in IITs, if you find or if you take note of it, that in IIT Mumbai, I had the opportunity to visit IIT Mumbai a few months back, and I have seen that they have already incorporated engineering physics as subject in their course structure. So I don't know whether we should go for that, considering the infrastructure, considering the other facilities we have in the department. what I have seen, I had the opportunity to be present in the HLI building where researchers, faculty members from different institutions, they have delivered their lectures. Most of the deliberations contains more scientific approach than the engineering approach and the technological approach. So the whole practice of chemical engineering is changing. From engineering, earlier we have seen from science to technology, technology to engineering. Now what we are observing, what we are seeing, that the reverse thing is happening from engineering to technology, technology to science, and then coming back to engineering again. So I would request that although it is a glorious journey for us, chemical engineering education and research in our country, but you should look forward taking the advices, experiences from people working in industry as well as in different academic institutions, not only in our country, but also in different countries of the world. With this request, I once again congratulate all of you for successfully organizing this event, this program, and we will keep in mind forever, at least for coming 20, 30 years. Thank you. Thank you very much.
I would request Mr. Alok Basu to kindly grace the dais. We are extremely sorry we couldn't accommodate earlier. Sir. So we would be glad if you could kindly say a few words. I would request Mr. Dipankar Das to share a few words.
It is a very interesting journey. I still remember 1983 with Siddhartha, the Diamond Jubilee. That was halfway through my engineering courses. And then here, 100 years, when Ranjana reached out and requested some of us to be part of it, it was a dilemma. Do I take this journey of 8,000 miles and come here? But glad I did. It was glad to meet my professors, eminent luminaries, whom I was very lucky to listen to, meet Rajat Babu. You know, with all your permission, Dean, FO, Rajat Babu, I think I want to first of all thank this organizer. It's not easy to do such an event, right? I mean, for months of preparation. I don't know when Ranjana first reached out and said, hey, we are going to do that. It was many, many months. Then Sudeshna writes emails. She was trying to get the organizing committee together. So, and when I come here, when I see the people running around, whether it's getting the food on time, whether it is getting, you know, all these different badges, it's a stupendous amount of work. Being in the industry, we sometimes are lucky because we are financially capable to buy that services, but when you do that services yourself, it's unbelievable. I loved hearing to the different sessions, but actually I loved most when I spent in HL Roy. Some of the students, the people who are going to do for PhD, some of the discourses, the researches they have talked about was unbelievably good. And sometimes I'll come here and I'll go back and rush to the other place because I love talking to them. one thing I want to say, and it's from my own experience of over 34 years, that I believe when you think of an outcome for yourself, one side is what you want to do, your passion, right? So follow your passion. If you follow your passion, nothing else matters. Second, the success is three-legged. One, of course, pedigree. Second is your passion, your drive, your hard work, you moving forward. And the third is getting a mentor. The gurukul you get in the university, the professors and the teachers, that does not end. When you go out to industry, when you go and do your PhD, you have to find a guru there, a mentor there. Having that right person is very, very critical, these three together. One of them doesn't matter. You can pass out of Harvard, you don't have your drive, doesn't matter. You don't find the right mentor in the path, it doesn't matter. And so just follow your passion and do the drive. The second, when I was talking to some of the people, the researchers, the presentations which come in, and I was talking to some of the industry people also, the industry doesn't reach out to you. So if you have a passion, if you want to do something, it's like marketing, right? Anything you make, you have to market and sell. So if you reach out to the industry, industry will come out and find one way or the other, right? Some people themselves may reach out through the contacts and everything. So I think that is something important I want to talk to. Any of you do your PhD, you do your thesis. I was talking to Ranjana, right? Many of my friends, like yesterday Rajiv was talking about, he's a professor in Florida, was the head of the department, and few other friends which are there, not from Jadavpur, even from my South Point, my school. A lot of work they do to actually market and get, so that's one of the requests to serve all of you here, is we need to think about that if you can market into the industry, all the great work, the great researches I was listening to, many of these are very, very relevant to the industry, very relevant to the industry. I'm in the oil industry for 34 years and never left the industry, never left chemical engineering profession, from Accenture to Deloitte to Reliance to Marathon Petroleum today. So if my request to the professors, to facilitate that how do we actually market ourselves, right? And go out to the industry. You'll go to 10 people, 9 may reject. One jackpot we hit, you get more funds, right? A lot of the things, I've seen some of my friends who are chair of the universities, they actually hardly get a chance. They say that, I can't teach my students, really, that's my passion, but they collect all of these. So one small request to the university is my request, because I see a lot of good things, good research being done here. And finally, as I said yesterday, I'm proud to be Indian. It's your dream, your passion can take you anywhere. And there are multiple proofs, and I myself have felt that, and that was my dream, to go somewhere. I've gone there, nobody could stop me. So just follow your dreams. Thank you very much.
We are extremely elated that our Dean FET, Professor Bhaskar Gupta sir, has joined us, and we would be glad to hear a few words from him.
My esteemed colleagues on the stage and all the august audience present here, it's my honor to be called here to say a few words. I'm not a chemical engineer. I am from electronics and telecommunication background, but Jadavpur University is proud of its heritage in chemical engineering. So as an ex-student of Jadavpur University, I am just sharing that reflected glory. That is my pride. We all know that 100 years back, chemical engineering started its journey probably as the first department of chemical engineering in Asia. Yeah. So Siddhartha, my esteemed senior colleague, like my elder brother, I just verified my information from him. It's for the first time in Asia. And what luminaries we had, even now we remember some of them. Yes, Professor H.L. Rai, his name is inscribed there as H.L. Rai building. but also we had people like Professor Baneshwar Das. I don't know whether some sessions were dedicated to them or not. Was it in this program? It was mentioned. I would like to request you to do something in his memory later. Very few people know about Professor Baneshwar Das. He was a contemporary of Professor H.L. Roy, and he designed and built up that Tala tank, another engineering marvel, not only in India, but in Asia, but all over the world, without a single nut and bolt. The tank was built up, and the total chemical technology engineering used there to purify the water and supply it over such huge regions more than 100 years back. That's unthinkable, unimaginable. Those are our forefathers. So I just share some reflected glory, and indeed that I could be able to share that here with you. I could come here, I could say these words, I could wish all the best to the Department of Chemical Engineering. I could wish that it thrive further and further in days to come. Makes me not only proud, but also really a harbinger of future. That's chemical engineering, Department of Jadavpur University, I believe, and one of the friends of chemical engineering. Thank you.
I would now request Professor Siddhartha Dotto Sir, ex-Pro Vice Chancellor of JU, to kindly felicitate Mr. Alok Basu, Secretary, JCEAA. Sir, we would be really glad if we could hear something from you.
আচ্ছা, আমি অনেক দিন পরে বলছি, কিছু বলার নেই। যারা বসে আছেন, যারা টিচার হিসেবে, তাদেরকে প্রথমেই জানাই আমার অভিনন্দন, রেসপেক্ট, সব কিছুই। এবং রঞ্জনা আমার থেকে বোধহয় 1 কি 2 বছরের জুনিয়র, অনেক জুনিয়র বোধহয়। যাই হোক, না আমি তো পড়াইনি, সেই হিসেবে বলতে পারবো না। আমি সিদ্ধার্থর সাথে ক্লাসমেট ছিলাম। হ্যাঁ, সিদ্ধার্থর সাথে ছিলাম। হ্যাঁ, ঠিকই। যাই হোক, রঞ্জনা এক বন্ধুকে এনেছিল, খুবই ভালো কাজ করেছিল 3-4 বছর, আমাদের থেকেও অনেক অ্যাক্টিভ ছিল, কিন্তু সে আর নেই। তারই এটা খুব ফিল করি এখনও। রঞ্জনা জানে নামটা, আমি বলছি না তার নামটা। প্রচণ্ড কি বলবো, দম ছিল অনেক বেশি। আমরা যেটুকু কাজ করতে পারতাম তার 5 থেকে 10 ভাগ, 5 গুণ থেকে 10 গুণ বেশি করতে পারত। যাই হোক, 2008 সালে এই আমাদের রিউনিয়ন স্টার্ট হয়। 2008 থেকে আজকে অবধি আমি এইটা সেক্রেটারি আছি, কিন্তু আমাকে সরাচ্ছে না কেউ, কেন জানি না। তা আমি চাই যত তাড়াতাড়ি ইয়ং জেনারেশন আমাদের থেকে একটু জুনিয়র, যেমন সুললিত খুব ভালো কাজ করেছিল এক সময়, 2013 বোধহয় সুললিত, 2010 সরি, আর 2008-এর ছেলেরাও খুব ভালো ছিল। তা একটা জিনিস বলছি, যেটা হচ্ছে আমাদের এখানে একজন এসছিলেন, সেই ভদ্রলোকের নাম ছিল সুললিত, কী নাম ছিল? ডক্টর ভিকে সরস্বত। ওনার ওখানে গিয়ে, আমি দিল্লিতে ছিলাম তখন আমার অফিসের কাজ নিয়ে, একটা অ্যাপয়েন্টমেন্ট করি, সুললিতকে ফোন করি যে সুললিত অ্যাপয়েন্টমেন্ট পেয়ে গেছি, তুমি আসবে। তো বললো স্যার আমি যাচ্ছি, কোনো ডিপার্টমেন্টের পয়সা বা কারোর পয়সার থেকে লাগবে না, আমি যাচ্ছি পার্সোনালি। ও আর এক বন্ধুকে নিয়ে গেছে, আমরা ওইখানে গিয়ে দেখা করলাম। আজকে যে পুরোটাই হয়েছে, উনি কিন্তু বললেন আমি 1 ঘন্টা থেকে 1.5 ঘন্টা বক্তৃতা দেব, মিনিমাম 150 জন ভালো ছেলে আসবে। যাদবপুরে কন্ট্রিবিউশন কি তিনি ওইটা বলতে চেয়েছিলেন, এবং বলেছিলেন কেমিক্যালের 50 জনকে রাখবেন, বাদ বাকি সমস্ত ডিপার্টমেন্ট থেকে আনবেন। এবং যা প্রশ্ন করেছিল ছেলেরা, তাতে উনি অভিভূত ছিলেন এবং বলেছিলেন সত্যি যাদবপুর ইউনিভার্সিটি কীরকম, কিন্তু আমি পুরোটা বলতে পারবো না। এখানে এমন এমন টিচার আছেন যারা আগামী 10-15 বছরের ভিতর যত বড় বড় অ্যাক্টিভিটি, মানে লড়াইয়ের জিনিস সব দেখতে পারবে, হচ্ছে তাদের কাজ। একজন কম্পিউটারের লোক ছিলেন, কম্পিউটার ইঞ্জিনিয়ারিং ডিপার্টমেন্টের, একজন ইলেকট্রিক্যালের ছিলেন, কেমিক্যালেরও ছিলেন 1-2 জন। তিনি সবার নাম ওখানে বলে গেছেন, সেই নাম বলার আমার অধিকার নেই। এই হচ্ছে কথা। তারপরে আমরা বড় বড় ইঞ্জিনিয়ারদের এখানে পেয়েছি, যারা বলেও গেছেন এবছর, তার আগেও বলেছেন সত্যি তারা কত বড়। এবং সিদ্ধার্থ আমার বন্ধু থাকা সত্ত্বেও, সিদ্ধার্থ তখন প্রবিসি ছিল, অনেক সুবিধা পেতাম কিছু কিছু কাজের জন্যে, তো হেল্পও করতো। ডিপার্টমেন্টের সবাই আমাকে হেল্প করতো, কেউই কিছু বলেনি। যাই হোক, আমি অভিভূত যে আমার এই ছোট্ট কাজের জন্যে আমি যতটুকু করেছি, আমি বিন্দুমাত্র গর্বিত নয়, কিন্তু আমি উপলব্ধি করেছি সবচেয়ে ছাত্ররা এবং টিচাররা তো টিচারই, তারা তো সবসময় সবাইকে ভালো বলেন, কিন্তু অনেক ছাত্রছাত্রীদের থেকে আমি শিখেছিও অনেক। সেই শেখাটা যারা সেক্রেটারি বা ওরা ছিল, তারা সবাই দেখেছে কিভাবে হয়, লেখা ফেকা কী করে করতে হয়। এই বলেই আমি বক্তব্য শেষ করছি।
Actually, just I want to mention I missed actually during my speech that 2 of my esteemed faculty members, Professor Abhijit Bhawal and Dr. Chanchal Mondol in particular, I want to mention. And I would like to get a big round of applause for them because of their big support to this event. And actually, I was mentioning so many names, I just missed them, but I felt that I must mention in particular, okay, because of their huge support. And not it is not yet complete. It will continue, I think, for the success of the entire event. So that's all. And also, Shamol Rai also has been supportive with us, and I must mention his name also.
আমি শুধু একটা জিনিস বলতে ভুলে গেছি, আমার এই দীর্ঘদিন কাজের সময় সাংঘাতিক হেল্প করেছেন স্টাফরাও, এটা আমি বলতে ভুলে গেছি, সেই জন্য আমি লজ্জিত।
I would request Mr. Ashok Nag sir, the alumni representative, to kindly share a few words with us. He's not. Okay, so if any of the alumni representatives are present here, we would be glad to hear. Sir, Dr. Sholit Bandyopadhyay, sir, you may proceed.
Thank you. I think it has been an immense pleasure to be here for these 3 days, and I think I came here on Saturday morning and came directly to the department and for the event. And I must say that there have been a lot of changes in the last 13 years since when I moved out of the department. And hopefully all the changes have been for the good. But as also Professor Siddhartha mentioned, that there are always issues and challenges and opportunities. And I think from having lived now 13 years in and around Norway and Netherlands and Switzerland in Europe, so to say, what I think we as a department, and always I feel connected to the Department of Chemical Engineering here at Jadavpur University, I think we need to work on a couple of areas as I see, and I would be very happy if I could also contribute with other alumni members who are residing outside India and working in academia. And one important thing that was also pointed out today in this valedictory session was about engineering moving more and more into technology and science. And this was something when I was graduating 2010 and working primarily within nanotechnology, there have been many opinions and advices of this being not a core area of chemical engineering, and thinking about it now 13 years down the line and what impact it can have on society, and especially during the pandemic times, I think it's more engineering than science. And I don't think these borders, and there was a very nice talk yesterday and the day before where we need to think about crossing these borders, science, engineering, technology, and also crossing borders outside from chemical engineering to other fields of engineering, and look at the fluidity of these different engineering streams. So one very important aspect is to stress on is work within interdisciplinarity, cross-disciplinarity, transdisciplinarity, however you want to call it, with different words. But it's very important to focus on more interdisciplinary work. And the second thing, and I'm very proud to say that there have been a lot of innovation, and I don't think we brand those the discoveries, the devices, the products that were once also sold from the department, including ice cream, if some of you would remember, and Abir, for example, during Holi, candles, and a lot of other innovative products, which we didn't brand them as innovation. But there is a lot of innovative activities, and having also listening to the technical sessions, there is a lot of ongoing innovation, but it needs to be properly, I think, shown, represented, presented, and reached out to people who can actually help in further funding and supporting those initiatives. And the last thing, which was also mentioned by Professor G.D. Yadav and many other luminaries during these 3 days, is that it's important to reach out if people don't reach out to you. So it's the same for students. It's an advice also for the younger faculty. I also have one of my batchmates who is now a faculty here. And also for scholars and PhDs, that it is not a problem to reach out to also to industries if you have some nice ideas, because that's the way, at least where I am now working, we have a lot of projects that are fully funded by the industry, and students get real exposure to industrial problems to solve in classes as well. And I think we are going there. There have been a lot of changes in the curriculum also in the last few years. And I think the next 100 years, as someone said, would be even more glorious than the last 100 years. But the foundation and the directions have all been very properly set by our forefathers, and also people who are our professors, our ex-alumni, and many of my teachers in the auditorium. The numbers are decreasing day by day, but that's how life is. And also the younger students. Please reach out if there is anything that, as an alumnus, I can contribute to this department. Thank you very much.
Now I would request Professor Shamul Roy sir to kindly say a few words.
Good afternoon to everybody. First of all, I would like to thank our respected Dean sir. Being a Dean of FET of Jadavpur University. He has to take care many important things apart from his excellent teaching and cutting-edge research. Nevertheless, he managed time to be with us. And I also would like to thank our respected finance officer, Mr. Gaur Patnaik, to be with us. And I am happy to join the centenary celebration of Chemical Engineering Department at Jadavpur University, which is the oldest chemical engineering department in India and Indian continent. This department was set up in 1921 with the help of with the help of P.C. Acharya and under the leadership of Professor H.L. Rai and Professor Baneshwar Das. Our department has completed 100 fruitful and glorious years, and I must congratulate all for this significant milestone. And I applaud, I admire, I appreciate for this development throughout this year. And at the same time, I urge all associated with this department to continue with the continue to move forward with same spirit, same dynamism and clarity of vision. The pain and sweat have into what the department today. Our alumni, our teachers, our staffs, our students, through the years with sincerity and commitment have contributed to the development of this department. I also salute the entire teaching community, the present and past, for their hard work and sacrifices. The students are the core of the department. The students are the heart of the institute, intellectual of our department, intellectual enterprise. And their success and in personal and professional will be the sign of a validation for this department, for this educational policy. I think our students' success success of our students, there will be no questions. Once again, I would like to congratulate all for this significant milestone. Thank you very much. Thank you.
As we near to the end of this program, one of our student representatives, Ronudeep Shaha, would like to share a few words.
Hello everyone and good evening. Today I'll just talk for a few moments as a representative of all the students who were part of this program through thick and thin. Now, well, after 3 long days of interaction, conversation, presentations among the luminaries of chemical engineering, the glorious centenary celebration is finally coming to an end. Though the 3 days passed in almost a flash, the rigorous preparation started almost 6 months back through a small meeting in our new seminar room. As students, it was definitely one-of-a-kind opportunity to be a part of this journey through thick and thin, standing side by side with our faculties, with our seniors, who are mainly the postgraduate students, and everyone. As chemical engineers, we are often taught to take multiple results, to take multiple iterations of results. And we had the opportunity to get the practical application while designing mere brochures, where we had to go through a lot of tests to finally produce the good one, which was circulated. Event management is quite a difficult task, and we are nowhere close to being experts. We are mere amateurs. At times, we had to be as spontaneous as any vigorous chemical reactions, and at times, we had to be patient while waiting for the centrifuge to be complete. Enough jokes. We are grateful to our noted faculties and seniors again for having faith in us. We have definitely often failed in our duties. We have been late at times, but it was really an honor to be a part of this journey. Definitely a special mention to all our guests, dignitaries, and speakers for embracing this celebration program. It was, again, a great learning experience for all of us, and we hope to be a part of such events in the future. Thank you.
If anyone interested among the PhD scholars or from the staff members are kindly requested to come on stage and share a few words.
Good evening. On behalf of Research Scholar, we are very grateful to be participate in this event. Sayantanu, Koustav done a lot of work, and it's difficult to mention all of the name. Also Suvanadi is here, Sritoma, Sohini, Pousali, and also from PDM Scholar and all of Saswato Vishwavidya, and also from CVCR Scholar. So everyone, the whole name is difficult during the sort of period, but on behalf of Research Scholar, we are very proud to be here, and future, after 10 years or 20 years, we are proudly say that we are part of this centenary program, and thank you so much.
Thank you. Now there will be the distribution of certificates.
নমস্কার মঞ্চ উপস্থিত মাস্টারমশাইদের আমাদের এফও সাহেবকে আমার নমস্কার জানিয়ে দুটো চারটে কথা বলতে চাই যে এই ধরনের অনুষ্ঠানগুলো আমাদের ছাত্র শিক্ষক এবং শিক্ষাকর্মীদের মধ্যে একটা সেতু গড়ে তোলে। এই ধরনের অনুষ্ঠানগুলো দরকার হয় মাঝে, কারণ যে যার কাজে আমরা ব্যস্ত থাকি, যার যার স্পেসিফাইড জব থাকে, কিন্তু এই ধরনের অনুষ্ঠানগুলোতে আমরা সবাই মিলে একসঙ্গে বাইরের সব মানে আমাদের অ্যালামনাসরা আসেন, তাদের আপ্যায়ন থেকে শুরু করে তারা কী করে ভালো করে থাকবেন, কোথায় থাকবেন, এই যে ম্যানেজমেন্টটা, এটার একটা শিক্ষা আমাদের ছাত্রদের হয়। এই ধরনের অনুষ্ঠান হোক প্রত্যেক বছর। মাঝখানে কয়েক বছর আমরা কারোর সঙ্গে কেউ দেখা করতে পারিনি, এই অনুষ্ঠানটা হয়ে খুব ভালো লাগছে। এই ধরনের অনুষ্ঠানগুলো আবার পরবর্তীকালে হোক, এই আমি চাই। নমস্কার।
Thank you, sir. Now I would request Professor Ranjana Chaudhary ma'am to kindly come on stage and distribute the certificates of participation of ICEIS 2023. I would also like to call Professor Papita Das ma'am to kindly come on stage for the distribution. I would be calling the names. Kindly come on stage to collect the certificates. Shohini Roy Chaudhary, Shourabh Bormon, Shritama Mukhopadhyay, Aparna Dhara, Paushali Chakraborty, Aparna Dhara, Shritama Mukhopadhyay, Orko Prabhu Roy, Shayan Mukherjee, Shondipon Bhattacharya, Bishwajit Debnath, Orko Prabhu Roy, Shayan Mukherjee, Bishwajit Debnath, Dinobandhu Manna, Kaustav Nath, Runa Shamanto, Shayantanu Mondol, Orundhati Sarkar, Sampad Sarkar, Shashwat Chakraborty, Aishwarya Das, Shomok Raj Banerjee, Shashwat Chakraborty, Shubhashish Ghosh, Joyshri Goswami, Ayan Gope, Swastik Paul, Shubhashish Ghosh, Hemant Singh, Anurup Mukhopadhyay, Debyarati Saha,